And today we'll talk about Apache Spark. Basic introduction we'll give it. Then we'll go into RDD. The first half of the session we'll go like little high level basic concepts about RDD. Spend time on scheduling, and then we will do resource handling. How does Spark internally handle resource handling? The second half of the session, Satya will walk through a lot more details. We'll go into the deep dive of RDD, where we go into lineage, how partitions are handled, different type of RDDs, how do you create custom RDDs. Pretty much we'll cover everything about RDDs in the second half of the session. So I think if you guys can come a little closer, it will help. Oh, you have a screen over there. Okay. So I conducted, there was a meetup actually, it was not official like a meetup. It was a Spark event which we conducted in Meetup Palace like 2-3 months before. How many of you attended? Okay. So in that was like more like a kickoff event where we said IBM is going big on Spark. So we announced that going forward, every month, we are going to do meetups which are a lot more in-depth. And this is the first of the series of meetups that we want to do it. So every month we are planning to conduct a meetup, especially on Spark, because there is a lot of investment that IBM is doing on Spark. So we want to create the general awareness among everybody that what is IBM doing and everything. So next month we will do SQL and data frames. So each of these meetups, the first half will be like very intro about what is data frame maybe. And the second half of the session will be very detailed hands-on sessions. Then we are doing streaming with Kafka. And IBM is big on analytic platforms. So our analytics platform pretty much depends on machine learning at a bigger level. So we do machine learning, graphics, and data sources. Each of them every month or something. So once the basic of Spark core and all the libraries are done, then we want to go into the use cases that IBM has implemented for Spark. Because we are doing Spark at different spaces. Analytics space, which major domains are using in IoT space, we are very big on Spark. So once we're done with this, then we want to discuss a lot more use cases, which will help people to get a perspective on how things are going on the Spark world. Before we get into the details, because I do want to get a pulse of how the audience are, so how many of you are like hardcore developers? Because based on that, we want to go into it. Okay, pretty easy. How many of you are already coding in Spark? Who are completely away from big data, who have nothing to do with big data, but you're developers, but not big data developers. Okay. So it's a mix, I think. Reason mix is there. So we'll start with very initial, very basic concepts for maybe 10-15 minutes. What is Spark? How is it different from MapReduce? All these things. At some level, we have to go into the details. But the goal of these meetups are, let's say you don't know anything about Spark, and you regularly attend these meetups. We are pretty confident you should get like a very in-depth knowledge on what Spark is about, without doing any homework. Let's say you don't do any homework, just come and regularly attend, you should get a hang of Spark. So having said that, let's get started. I think pretty much most folks understand, because your big data world is pretty much a big chunk of the folks here, we understand what does a MapReduce do. At the same time, we want to tell what are the basic limitations. A few minutes only we'll spend on all these things. So MapReduce, a lot of boilerplate code are there, so which makes the code complex. What we mean by that is, let's say the standard thing, right? Any big data world, when we start, we say word count example. So when you write a word count example in MapReduce, in Java, you'll end up writing maybe like 50 to 70 lines of code. So in the case of Spark, we use Scala extensively in the Spark development. You will exactly write the same word count example in 3 lines. Believe me, it's exactly 3 lines. That's all it is. So the code is a lot more crispier. The boilerplates are completely removed what you used to have in MapReduce. The second one, disk-based approach, not good for iterative use cases. So MapReduce, let's say you have a task. You run a map card, what does it do? It takes some input, does some processing, it writes to an output disk, right? In the case of iterative processing, if every time you're going to write to a disk, it's going to be quite an expensive operation. There's a disk IO involved, storage is involved, storage has to be replicated, that is involved. You have to serialize the data because you're writing to the disk. All these complexities are involved, which has a performance impact directly. In the case of Spark, let's say you have a job where you run like 5-6 tasks together as part of a job. What it does is each of these tasks are actually in-memory operation. There is no disk IO involved, so the rest of the problems which I mentioned will not exist. That's another thing. Batch processing not fit for real time. So we all know MapReduce is pretty much basic for batch processing, right? So if I have to do anything with real time, MapReduce go in this direction, what happened is there are so many technologies which keeps coming up. If you see MapReduce, there was a batch there. Then they said, I want to do interactive. Then Impala came up, Thais came up, Drill came up. Then we said, okay, I want real time. Then Storm came up. The amount of frameworks which came out is actually chaotic. And sometimes it's impossible to manage actually what you're doing. So what is the ideal situation, right? So you want the ideal situation is I write some chunk of code. So let's say I wrote a MapReduce, something I wrote in MapReduce. Then I decided I want to do this not only in batch, but I want to do real time. What you would have done is you would have picked up Storm. Maybe OLTP in some use cases, you would have picked up. So, but you have to end up rewriting the entire code what you wrote for MapReduce in the case of Storm. That you have to do. There's no option. So next, let's say now you have real time and you have batch. Then you decided I want to do interactive query. You can't do anything. You can't leverage both. You have to now write the entire code in either Impala, Thais, Drill, or any of these things. So the same code, same functionality. If you want for different use cases, you end up rewriting the complete thing. That's a key problem. Actually, just to check on this one. So don't you play very formal. This is a meetup. So fire questions at any time, stop any time. You want to give it very interactive. The session will be very boring. Okay? So now this is where Spark comes in. So we mentioned, okay, 3 use cases are there. We write a code we want to use in 3. This 3 is completely possible in the case of Spark. Spark is a general purpose engine, general execution engine. When you write one code, let's say in the batch mode you wrote it, you can actually reuse that same code in the real-time use case or in the streaming use case. So that is pretty much it. But yeah, so there is underlying the core of Spark. If you see, there is something called Spark code, which is underlying the basic one. Spark code is batch and interactive. So let me put it. Okay. In Spark code, you can write a job where you can submit as a batch mode, or you can make it interactive at some level. The next comes Spark streaming. You wrote this code in the batch mode, so that means some amount of code you have written. So I'm reading a file from somewhere, I'm doing some bunch of transformations, and I want to spit out a result. You wrote it in the batch mode. Now we want to plug the same thing into streaming. There is a concept of a D-string, which may not go into much, but assume the same code can be stuck into a stream and it can be. The queue can be anything. It can be a Kafka queue, RabbitMQ queue, but Kafka is supposed to predominantly in Spark, and you can plug it in and it can run a stream. The same case, if you want to do interactive, there are some challenges in interactive, which I'll explain a little later, what are the problems, but it's very much possible for you to make it interactive. So then, the next 2 things which Spark is very good is graphics and ML. So today, in addition to the 3 things that we explained, if you want to do machine learning, what the generally companies do is, they end up writing their own algorithms, right? ML algorithms, they create their own algorithms, and they actually create their own pipeline. That's pretty much a very standard. Right? So let's say you need some basic set of algorithms, some 40, 50 algorithms that are used more often. If there's a use case like that, you don't want to end up rewriting all the time. And you want to leverage whatever the existing algorithms, and you want a place where these algorithms keep growing, right? And you want some basis to say, I need a basic pipeline framework, which I can just use these algorithms in. That is available in ML. ML gives you a way to run machine learning pipeline, where you can use the standard algorithms provided by Spark itself. So machine learning algorithms are pretty linear algorithms, linear pipelines, that's one of the problems. But when we go to the machine learning session, actually we will explain how IBM is leveraging the underlying Spark machine learning pipeline to create our own ETL type of pipelines. And that actually we are trying to open source now. Similarly for graphics, a lot of algorithms are available which you can use. The next thing is, some more concepts about the difference between MapReduce versus Spark. In the case of MapReduce, the basic thing is, there's a process which comes up, right? So you read something, do some processing, and done. For every task, there's a process which comes up. But in the case of Spark, if you see, there is, when you submit a job, there is one process which comes up. Inside the job, you can have 10 different tasks or 100 different tasks, it doesn't matter. It's the same process which is up for each task, it spawns a thread and process thread. So the key difference is, there is a lot of overhead when you start a process for every task. So let's say there are 2 different use cases, right? One, I have a big task which I want to run. There is only one task. There is one use case. But there's another use case where I want to start a job, but I want to run a lot of small tasks more often. There are use cases like that. Second use case, if you go for it, MapReduce will not work actually because it will work. It's not like it won't work. The overhead on it is too high because coming up and starting a process and killing every time is quite an expensive task. I think at this point we say, okay, Spark can solve most of the problems, right? So it's really Spark is like, will it solve everything where there is no problems at all? It's not really true, some level. So I'll give you one example before I jump into these things which are there. Let's say Spark is not like, can it replace Impala? Maybe not. Can it replace HBase? Maybe not. There are specific use cases for which these tools still show an edge over Spark. Let's say I have a 300 terabyte data against which I'm querying. The filter criteria is exactly one column I have. HBase will do much better than Spark, believe me. If I have one particular table and I want to do different slicings of it, of the same table, that means n different filter options, but there's only one table, Druid will do much better than Spark. So if I have a couple of tables, but I have a lot of ad hoc queries running here at the time, that means I'm doing a full table scan every time. Impala will do much better than that. So if you're not telling Spark will solve the global problem of all these problems, if you're not telling. There are majority of the use cases Spark can fit. At the same time, there are niche areas where Solar can show much better performance than Spark. So we're not telling that Spark will solve the entire thing and all it will get around. That's not the goal of it. So applications cannot share data. So we'll go into underline what is RDD, because at this point, if I say, you may not understand. But assume there is a data structure within Spark. That's called RDD for now, for this slide purpose. If I run two different applications, within an application, we said everything is done in in-memory operation, right? Now I have two Spark applications which are running in. I want to share data between these two applications. It's realistically not possible for you to share unless the first application writes it to some disk and the second application reads it. That's a major problem of how Spark is designed. Spark is designed that way itself. Resource allocation inefficiency.
Excuse me, can you repeat that? Can you repeat that what you said?
Sure. So let's say you start an application. When you start an application, it starts a couple of jobs, a job or a couple of jobs. So in that, you run a couple of transformations. Okay? Each transformation is actually a task. Now there is within this job, you can share all the data, because that's how the memory abstraction is designed. But I want two jobs which are running in, and I want to share data between these two applications. It's realistically not possible to do it in memory in the current architecture of Spark. You have to write it to a disk, and the other guy reads it on the disk. That's what it is. Second one is resource allocation inefficiency. We'll actually go into a detailed topic in my topic later in the session. I will talk about what is the problem. But here I want to tell you a brief idea is, when an application comes up, it works with the cluster resource manager, like Jan or anybody, and tries to get some executors to work on it. Once it gets some executors, those are actually fixed to that application. That's very important. It's very much fixed to application. It cannot release till the application goes down. This is pretty much a use case before Spark 1.2, you can say. In Spark 1.2, they introduced a concept called dynamic resource allocation. We'll go into a little bit, but that doesn't solve all the problems. It solves one specific use case, maybe a shuffle use case it solves, but still the rest of the use cases remains the same, that once an executor is allocated, it's very difficult for you to release the executor. We'll cover in detail actually, I just want to give you a high level view of it. Not exactly designed for interactive. This actually, we started facing this problem like a month back in IBM. So what happened is, you wrote some code, right? So if you, I'm not sure how many of you have done Volt or Impala or any of these things. So where, if I want to run interactive, all I need is a JDBC connection and then 5 MySQLs, I can do interactive session. But Spark, in addition to the SQL itself, you should be able to do a lot more things interactive. But it's realistically not possible, because it's actually like a jar which you want to submit in the back. That's how Spark works. So there are a couple of open source has come in frameworks which help you to do interactive. One is very famous, one is which is created by IBM called Spark Kernel. Actually, it's an open source which we are trying to enhance a lot more than one. That is basically Spark itself doesn't give you a very good interactive if I have a middleware. Let's say I'm writing a microservice architecture on the top of it, where I'm getting some events from either a API level or from a UI or anything, and I want to do interactive. Basic Spark doesn't give you an option to do that. But there are some frameworks, two things are there. Job Server and Spark Kernel are two of them. Spark Kernel is owned by IBM. Spark Kernel is a much better fit. We can go into these details also a little later.
Excuse me. So, in case of executor failure, so though it maintains a lineage, so will it transfer that to some other executor?
We'll come. Hold your question. I have another 20 minutes or 30 minutes. I'll go deep dive into that.
Yeah.
Okay, hold your question. Anything about basics? Because after this, we are going into RDD, and we'll be mostly talking about RDDs, scheduling, and job. So if you have any high-level question about it this time, we can take it.
Hadoop was designed to run on commodity hardware. Now Spark comes into picture, and in-memory processing is the top actually. In-memory processing costs more, right? You have to invest lots of money in RAM. So how is that compared running with cheap hardware, but I don't think Spark can run on cheap hardware.
Okay. How many of you think Hadoop can really do very good in commodity hardware? Okay, the definition of commodity hardware is like abusively used actually in the industry. If I give you a hardware which is like 4 GB RAM or 2 GB or 1 GB RAM, MapReduce cannot do anything much. So leaving apart that, I'll come into the details of it. So Spark doesn't say exactly I will work good on only on in-memory. It will do too good on in-memory. That means the numbers will show, and I'll explain why also. If you're completely in-memory, it can do maybe 100x more than faster than MapReduce. But if I'm not in in-memory, I will still do 10x more than this one. I'll tell you why. So there are key things in this difference, right? So before Spark, I think 1.1 or 1, before that it can work only on in-memory. There's no way for it to fall on disk. But after a particular version before, Spark can actually dip into the disk and come out of disk. That's very much possible. So the key difference here is, when I run a transformation, when I run a job, there are some basic difference which you need to understand, maybe a lineage, which I have to explain in RDD. When I do some operation, it doesn't do the operation at that step. I'll give you a small example. When I load a file from HDFS, I do a filter, then I do another filter, then I do a map operation or something like that. In the case of MapReduce, it actually executes each step in that place.
You're talking about lazy execution, right?
Correct. The execution will show a big difference in architecture. When I do that one, when I'm dipping into that disk every time, I have a very expensive, I'll tell you the problem when you're telling memory is a lot cheaper than network bandwidth. In the case of MapReduce, I'm writing into the disk. So there's a storage involved, which is heavy storage. That means 1 terabyte file. When I filter and I produce 900 GB, I had to store 900 GB. And then I made out to do replication if I want to do replication. I had to serialize the entire 900 GB and write it. Serialization is expensive. Disk I was expensive. Network bandwidth is expensive when I'm replicating across. So these problems will not be there even though. So without doing in-memory, I will still do Spark will do roughly 10x better than MapReduce. Any other questions here? Okay, we'll jump into RDD. What is RDD? RDD is resilient distributed DataSet. This is actually the key innovation you can say for which Spark was very successful. This is everything about Spark, pretty much basic of Spark is this one. This is a memory abstraction given to that where you can do in-memory computation in a distributed fault-tolerant manner. That's pretty much what RDD is. So it is lazy immutable. We'll go into what does that mean. It's lazy. That's what I was trying to explain. When I load a file from disk into in-memory, that means I create an RDD out of it. Thereafter, when I do any set of operations, let's say I loaded a file, then I want to do filter, and I want to do map, then I want to write the output to the disk. Usually in the case of MapReduce, what I've done is, when you say a filter, it actually executes a filter operation. When you say map, it actually executes a map operation. In the case of RDD, till the action comes in, action is something like where I had to either return the result or write to a disk or anything like that. Till that place it hits in, it doesn't do anything. All it tells is, it notes down the lineage that I have to do all these things before I hit an action. Only when it hits an action, it goes ahead and runs the entire set of information. A lot of benefits of this approach. One is, what I have, when I for fault tolerance, maybe I'll explain when the fault tolerance comes in. So you understand lineage, right? So the next thing is immutable. Any system which needs to scale, basic rule in architecture, we know it has to be immutable, otherwise scalability will be a problem. So RDD is immutable. Fault tolerant. So any system that we are designing, that means that the storage-based system, the first thing that we'll ask is it fault tolerant, right? So before we go into how Spark does fault tolerant, we'll discuss about what the traditional systems do Spark fault tolerant. In the traditional way, before RDD came into the picture, if you want to do fault tolerant, what do? You'll either replicate the entire data in a couple of places. That's one way to do. Or you will do is replicate the log of dates that you had it, so we can replicate. These are pretty much the two standard ways that you can do if you want to do fault tolerant. But in these two cases, all the things are a problem. Storage is a problem, extra storage because you're getting disk writes is a problem, serialization can cause performance, network bandwidth is a problem. But in the case of RDD, how does it do fault tolerant is, if I do a set of transformations, it actually doesn't replicate anything. All it notes down is just the lineage that I have to do. That is the only thing which is noted down. So at any point in time, let's say I load a file, I do filter, and I do map. A particular partition in map actually fails down. It knows how to calculate that particular partition alone from the parent RDD's partition. That's all is there. That's all is stored. So it's each of the partitions know how to derive its data based on the lineage from the parent RDDs. So the data, all the problems that we explained in MapReduce or any other fault tolerant systems will not be there for transformation RDD2, then RDD. In RDD3, if one partition fails in, it will just go to RDD2 alone to get that one. That's all it will do. But if you're going to go, let's say if you don't have persisted information on RDD1, then it will go back. It depends on at what level I can get the data. If I cannot get the data, let's say there's a failure on that one, then I can go back and knows how to calculate one data.
Excuse me. This lineage information, what you're talking about, right? Is it the persisted information? Because if it is still in memory, I can definitely lose the data.
Hold the thing. The second session will go a lot more details about lineage. You'll know everything about lineage in the second level session. Because at this first part, I want to just keep it slightly high level so you don't get lost. Because if I start diverging into the detail, I may not finish the first session, but you will get your answers. Hey, go ahead. Yes. Sorry,
the question was if the node which contains the lineage, if that goes down, how is that handled? Probably the same question.
Correct. So I got what you're telling. The second session, hold on your thought for the second session. We don't want it, because if I keep jumping in more details, the second session will become redundant. So Satya will walk you through a lot more details on those things. Lineage, partition, completely you hold your thought. Partition. Partition is about, so basic of Spark is I distribute and do run the process, right? So when I have an RDD, I say create into 10 different partitions and run all 10 of them separately and produce it. Very standard distributed processing is what it can do. So since many of you haven't seen a Spark one, this is pretty much like a standard, very simple Spark one. It loads a file, it does some filter operation, it does some map, and it is saved it. So what will happen is at each step when it does any transformation, it actually produces a separate type of RDD. It means when it loads a file, it creates a Hadoop RDD. When it does a filter, it creates a filtered RDD. Like that, it doesn't. So really what will happen is, oops. It actually starts with the action, as you mentioned. So it goes to the output of it, and that time it realizes, what should I do? I need a map value. Then it comes to map, and map realizes that it will filter. That's how it goes and starts from how the file is loading. From there, it keeps processing it. So we'll show a lot of hands-on session. Just get a hang of it, where if this happens, then it starts with the action, and then it tries to go each of the transformation that it needed to produce that action. Now I'll dump a little more started going into the details about how dependency works between RDDs, and then we'll explain this. I'll go a little more depth. So if you have any questions on this one, we will go details now. There are two types of dependencies which you want to know in the case of RDDs. One is narrow dependency and wide dependencies. So what is narrow dependency? Each partition of the parent is used by at max one partition of the child. So before we walk into it, let me explain some level about stages so you understand what it means by that. So let's say I load a file, then I do a filter operation, a basic filter, and then you do a map operation and then write into the output. At this case, when a filtered RDD is produced, each partition of that is accessed by only one partition on the map. Map is a child RDD here, the parent is filter. Each partition of the filter, it will produce actually one and only one partition for the child. That is what we are telling narrow dependency. When it's a narrow dependency, the underlying Spark, what it does is it just pipelines a sequence of information as one single stage. We'll go into stage also. What is stage? All those details will go. But just get the hang of it. If my parent partition has only one dependency, there's one-to-one mapping between a parent partition to a child partition, it runs as the entire set of transformation can run as one stage. But in the case of wide dependencies only happen when you do a shuffle operation. Wide dependency tells that, let's say you want to do a count of the starting letter of a name, or count of anything. Count of some operation which will result in a shuffle and similar to how MapReduce does. That means you have 10 different partitions after the mapper output. From there, you want to group all the names starting with a particular letter to one particular, how the reducer combines it. In that case, a child partition actually depends on more than one parent partition. If that use case happens, it's a wide dependency. That level, you got to hang out what is wide and what is narrow dependency, right?
Please repeat that.
Sure. So Narrow dependency is each partition of a parent is used by at max one partition of the child. What we are telling is, let's say there's a filter, first operation transformation is filter. Let's say again next is also a filter. So when a first filter happens, it produces a number of partitions. The child actually depends exactly on that because it's going to work only on that particular partition which the parent filter. So the dependency on the child is only on the output of the parent on that particular partition because it's working on the filter's output alone. But in the case of shuffle, you had to really shuffle all the things on the mapper side to bring it to a single node on the reducer to do any function. The regular MapReduce concept, right? So here also we have GroupByKey, ReduceByKey, similar concepts of MapReduce. In that case, a child depends on n number of parents. That means when I have to create the lineage back, in the first case, I just go to my one parent and create the lineage and derive it. It's a lot more simpler. But in the wide dependency or shuffle dependency, I have to go to n different parents to create it, and that is a lot more complex. The complexity increases the moment I have to track the lineage for wide dependency. This is the underlying code. I just put the class diagram for underlying Spark. How does wide and narrow dependency happen? So if you see there is only one concrete class they have for shuffle dependency. There's nothing much there. There's only one way it can do. But in the case of narrow dependency, they actually have three concrete classes within Spark. One is called one-to-one dependency. The other one is a range dependency, and the third is prune dependency. So let's see what are these three. All three are actually narrow dependencies. So what we are telling in the narrow dependency is, the definition is little more, pay attention to the definition. Each partition of the parent is used by at max one partition of the child. That means there can be use case where there is no child also. That's also very much possible. That still comes under narrow dependency. In the case of one-to-one dependency, what we explained before is one-to-one. I have a filter, when each filter produces one partition, the next transformation is still a filter. I mean there is exactly one parent has one child. That relationship is one-to-one dependency. The second one is prune dependency. Prune dependency is, let's say, so the way you partition is actually there are different type of partitioners which are available based on which you can partition. So Spark provides you with, I'll pick up an example, range partitioner. So if you do a range partitioner, let's say the parent has done a range partitioner and it has provided 10 different partitions. The partitions are starting with 0 to 10 is 1, 11 to 20, like that, there are 10 different partitions. Now when the filter comes in, and the filter says, I want to get this field which are greater than maybe 30. If that's a use case there, it doesn't have to go to every particular parent to derive it, because it already is created based on range partitions. So the system underlying knows that I have to go for specific partitions alone to derive my information, rest of them are not there. I prune the rest of the partitions. That's prune dependency. That means I don't have to go every parent to derive it. Because when I say filter specific, above 30 or 35, I know that from 30 only I need to prune, the rest of them I don't have to. That's what the prune dependency is. Third one is range dependency. Range dependency says, I have a group of child partitions, it depends on a group of parent partitions. There's no exact one-to-one mapping, but there's a group of child which depends on a group of parent. I'll give you an example. So best is union. So let's say there's an RDD1 which does a union with RDD2. And the RDD1 has 10 partitions, RDD2 has 5 partitions. Here the basic assumption is, let's say these two have different partitioners. Okay? Now when we do a group union, what it will produce is, it will produce a partition 3 with actually 15 partitions in this use case. In this, what it will do is, it won't do any shuffling information, no moving of data, nothing happens. It just concatenates and gives you in this case. The partitioner information is lost because each of them are different partitioner originally. So what partitioner the third one will have is completely lost. It's up to you to create a new partitioner and reorganize the data. But there is another union there. Let's say in the same case, there is an RDD1 which has 10 partitions, and RDD2 also has 10 partitions. But the partitioner information, partitioner is exactly same in both RDDs. If that you produce a union, it won't produce 20, it will produce 10. So because the partitioner is same, Spark understands that I need to just pair up these two partitions and produce a single partition. That's slightly different, how the union itself works within Spark. That comes in the example of a range dependency. When I have group of partitions on child, I depend on group, I don't know which group it is. Based on use case by use case, the range dependency will be better.
I have one question. So what you're saying is I can't decide what partitioner I'll have to use with a particular RDD?
Correct. If you want to produce a different results. So these two will produce produce different results. Because if you say that two RDDs that you are using it to produce a union, if there are two different partitioners, Spark doesn't know how to interpret them. So Spark, what it will do is I'll just combine everything and give it to you. Because there is no intelligence it can apply over there. But if you say those two partitioners are exactly same, it uses the intelligence to pair them. That's the key.
So, excuse me. So, how we can identify that both partitions are exactly same? Is there any criteria?
Oh yeah. So when you decide the partitions originally, you say what partitioner you want to apply on them.
Okay, based on the partitioners. Okay.
Partitioner that you applied on, that is what the things.
Can you give a simple example of prune? Simple example.
So prune is the one which I said, right? There is a range partitions, then you apply a filter on that. It doesn't go through all the partitions, only specific partitions it picks up, rest of them it automatically drops because it knows against what key and prune. There are 10 partitions, 0 to 10, 11 to 20, I give you an example where I said if I want to do filter above 30 or 35, it knows that I don't have to do, I can prune the first 3 partitions because mine is above that only the range is coming. Because it's clearly the partitioner is range based.
That's omitting.
Exactly, omitting is a prune.
I kind of feel that the prune and the range is a little bit, there is some sort of intersection with creating the partitioner itself. Because for the prune, you still have to set the range, right? Okay, fine. The partitioner, you put 0 to 10 in a particular partition and 10 to 20 in a particular partition.
I just give you an example.
Yeah.
So that's not the only use case. So,
Okay.
so I just give you an example where it can prune, but that's not the only use case. Anything where the underlying the scheduler can know that the execution decides that I have pre-information based on which I can prune some partitions.
Okay.
Anything. Just give you an example of the partition. So this is about job scheduling. So we'll go into a little more details about when you submit a job in Spark, what does underlying happens. So that is very key when you want to understand what's happening. So that you write a Spark program. The program that you write, where it runs in, is called a driver program. So always the program where the node where the program runs in is a driver program. It can execute it on a cluster, Spark cluster. So the driver program is very key because it runs a lot more process than the driver itself. It runs something called that scheduler, task scheduler, all these things. We'll see what is the difference. So when a program first comes up, the program actually an application can have one job or n jobs. So how do you define what is a job? When you do an action, there are 2 set of things that you can do in Spark. One is called transformation, one is called action. Whenever it hits an action, Spark internally treats that like a job. In one application, you can have n different actions, and it will treat them as n different jobs. The criticality for a job is, when I see an action, I create it as a job. That's the first thing. Once the driver identifies a job, it actually gives the job to the DAX scheduler. There's something, a process, another process called DAX scheduler, it gives a job. So what is the responsibility of a DAX scheduler? DAX scheduler takes a job, it identifies how many stages are there. That's all a DAX scheduler does. Now we need to know what is a stage. The stage is when I don't have to do a shuffle operation in my entire suite. If, let's say 2 examples. One example, my job, I load the file, and I do a lot of transformations, but none of them result in a shuffle. If that's a use case, DAX scheduler will result as a single stage. Straight away, the narrow dependency will do a single stage. But wherever there is a use case where there is a shuffle happening in, it treats that like a stage format. Let's say we have a filter, we load the file, we do a filter, then we do a group by, and then we do some set of operation. The group by will result in actually a stage boundary because there is a shuffle happening. So what Spark will do is, the first till the filter is treated as one stage, and after the group by is treated as another stage. So it will identify the stage boundary. Let's say after the group by, I do 2 filters, and again I do another group by. Then there is another stage boundary created that will result in 3 stages. You got to hang out with the stage. So the stage is nothing but wherever there is a reshuffle of data.
Shuffle is the only one parameter for stage boundary?
Correct. Any place where a shuffle happening, reorganization of data happening, that's the only parameter for stage boundary. Because otherwise it can pipeline. So for Spark, pipeline is very easy because there is a direct dependency one-to-one partition, it can do very fast. But everybody knows when there's a shuffle, it's an expensive operation. Same as in the case of Spark, because it has to pull data from everywhere. So now the DAX scheduler job is, once I give a job, I will create n number of stages. That's all a DAX scheduler does. After that, it takes the first stage that it created, gives it to a task scheduler. The responsibility of a task scheduler is, once I create get a stage, I create a list of tasks. So what is a task? So let's say we do a filter. We loaded a going to do is a filter. So each partition data with that filter together is identified as task. That's a key definition. So what the task scheduler do is, it keeps on creating tasks for the given stage. Let's say when you loaded, we had 10 partitions, you would have created 10 tasks.
I have one question. We talk about this particular task, right? But don't you think it should be the transformation plus the action plus the partition? Because the task is triggered only when there's an action. There's no point in executing the action after the transformation. It's best to execute it as part of the transformation itself. When you say task, you said it is a partition plus transformation.
Sure.
What I'm saying is, why should not be the partition plus transformation plus action?
Okay, okay. I'll come. Hey, is it? Okay, can you guys hear me?
Yeah.
I think my voice is too loud maybe. I don't know this. So to come here, so what is an action? Action is the last step. For our case, writing into HDFS is last step. But in the first one I loaded it, I do first one filter, I can do another different filter, and I can do another map, then finally is when the action comes in. So I have to go in the same order of sequentially executing till I reach there, right? So that's why it has to do the first thing. So once a task scheduler creates a task, the next thing what it does is, it negotiates with the resource manager to get some executor to actually run this task. That's a key. So let's pick up an example where you have 5 partitions and you have 3 nodes. That's all you have in now. And each node, let's keep it simple, where it is a 1 core per node. Okay? So maximum you can at a time process only 3. That's the use case, but we have 5 partitions. Okay. So now the task scheduler created 5 partitions. First thing what it will do is, it will try to see if the executor which has the partition information, is it free? So that data locality is ensured. It identifies that. If it's free, it gives it. Let's take the first 3 partitions. It straight away found 3 nodes and it gave the data and it's scheduled. Now what will happen is, it will wait for the remaining 3. It won't do anything, it will just wait till the entire 3 is done, because it doesn't have any more resource to execute. Now let's say the first partition, it actually completed, the first executor completed. But the fourth partition is just to go in there, the data is not available in the first one. Let's take for example, or let's keep it simple. The fourth one is there, fifth one will say it's not there. Okay. So fourth one says, the data is actually available in the first executor itself. So the first node got done, the fourth one goes there, and it executes it, very simple. Now the second executor finished it, but the fifth partition which is going to go there, it's not locally available. It's only in the third node it's available. What Spark does is, there is a configuration variable inside, which will say how much time you want to wait to see if the third node executor is done. There's a fixed time slot, it will wait. So if it will wait for the fixed time slot, if it is not available, it will go on and schedule into, and it will do a network bandwidth. It will pull the data from 3 into and run. But if between the time interval where it's waiting, if the third executor completes it, it will schedule it over there. That's pretty much what it does internally. So with this, we have some level done scheduling. We'll go into how the resource allocation happens. We want to open up for questions if you have
I
any
have one
questions.
question. The DAG scheduler and the task scheduler is part of the Spark code.
Yes, very good. The entire thing is part of Spark.
Can you explain the part where the nodes are waiting? Like the executor waits for some time and then it's not there.
Correct. So whenever it's trying to schedule a task, the key thing is, in any big data setup, you want to have your data to be, data locality should be ensured. It's very expensive to move the data across a network. That's a standard problem, right? Every system does the same thing. So what Spark does is, it tries to identify if it is there. If the data is not available, but the executor is free, it doesn't want to immediately update, because maybe it's possible in 3 milliseconds, the next one where its data locality is available. So it just waits for the small amount of time which is configurable for you, but it will do. If it has crossed the time limit, it will move the data perfectly fine. And there's a standard principle how it applies in any other system. It tries to allocate within the same rack. It's not there, then across the rack, across center, colos. That's how it is. Standard, that is very good.
So in waiting time, does it transfers the data or does not?
Which one?
During the waiting time, does it transfer?
No, it doesn't transfer. The key for the waiting.
Because if it transfers, then it might be helpful if the local resource is not available.
Actually, that defeats the purpose of the wait time, right? Yeah. So because the moment you are transferring, you're consuming huge amount of network bandwidth. That defeats the purpose for which you're waiting. So there are a lot more tasks which are running in. They will also need bandwidth, right? The key thing what what you want to avoid while you are waiting is you don't want to suck in the network bandwidth. In fact, the most expensive in a cluster computing is the network bandwidth. That is the reason which you want to save for which you are waiting. So now when you start doing it, then as well you don't have to wait also, right? That's it.
What's the duration of wait?
That's configurable for you. It's a setup, couple of it's up to you. You design what you want to set.
Are you saying that the task scheduler ensures data locality?
The task scheduler, the executor actually when it's executing it, that is what task scheduler will assign.
So the task scheduler should know which executor has
the
partition.
data, yes, exactly.
So that does it maintain something like a map or something like that showing that this partition is on this executor, and based on that
It has that information, but I don't know what data structure. If you're asking the next question where the data structure maintains, I don't have an answer. But task scheduler knows the data.
Because in the name node it maintains the block map and everything.
Correct. There's nothing like that directly yet, but the task scheduler knows the patch. Actually, I can give you a little more detail towards the end of the session. Let's discuss. I'll tell you what it is.
Who manages the task scheduler?
Which one?
Who manages the task scheduler?
Each of the process goes in the same way. Its own. There is no master which manages the master for everything is the driver. So starting guy.
So how do they know they are working on same data set?
Oh, so the task scheduler completely works based on what the task scheduler gives. The task scheduler doesn't do anything other than instructed by the tag. The task scheduler works purely based on what the driver gives. It's like a pipeline of operations. So it doesn't depend on anybody else, then the parent will give the data. It works with the sequence. The driver starts, gives the job, task scheduler picks up, gives the stages, task scheduler picks up, creates task. That's the sequence.
So for each and every driver that we a DAG scheduler, or there's one DAG scheduler for multiple drivers.
Each driver has an action.
So it's
independent. Completely a job is independent.
So the prerequisite is that the data is already distributed, right?
Correct.
So if we use Spark for streaming data, when the data is coming from outside, does it need to be distributed first before Spark can work on it?
So in the case of streaming, there is a slightly one level of abstraction. I'll just spend 2 minutes. There's one level of abstraction on top of IDE. The whole concept of Spark works on IDEs, right? So in the case of streaming, but RDD is very specific for one particular data set. But in the streaming, I'm getting like a stream of data sets. So Spark created one level of abstraction called D streams, which works on top of a list of IDs. So assume stream is like a block of information keeps on coming in. For each block it creates an ID. There's one level of abstraction they created called D stream. So any transformation that you are doing in a stream, you will do it on D stream, not on ID. So then they know how to convert the D stream to ID, which is a very simple abstraction.
So data will be there.
Executor is data localization applies for the executor. Why? Because we are telling that the network bandwidth is in a very fast operation.
Yes.
So if the executor is not data localization, then again network bandwidth comes into.
Correct, that's what I said, right? When the executor picks it up, it first ensures that there is data locality, it will try to pick it up. If it is not available, that's what I said, it will wait for that particular amount of time. So the goal of an executor is it will always try to execute with the data locality. That's a goal. Resource allocation. So I think initially in the talk I said we'll go into the details of resource allocation. This is the time we can discuss more. So what is resource allocation? So resource allocation we can discuss in 2 splits. Before Spark 1.2, after Spark 1.2. There is a big change between in Spark 1.2 which happened. Before Spark 1.2, let's say a job comes up, an application comes up, and the application says, I want this many executors to execute my application. So let's say you got 10 executors to execute your application. What will happen is till this application dies, those executors are exclusively assigned for you. What does that mean is, let's say as part of the application processing, you don't need 2 of the executors anymore. You're keeping it idle for some reason. It cannot be released back to the general resource pool where any other application can pick up. It is not possible before Spark 1.2. It's actually exclusive, dedicatedly assigned only for you. This is a very big problem. When you're doing multi-cluster, multi-tenant environment, this is a big problem. So in Spark 1.2, they solved this problem at a particular level, but they didn't completely solve this problem. I'll tell you what they solved and what they did solve. In 1.2, what they did is, they will allocate resources. Okay. So in 1.2, when an application comes up, there is a capability for it to say, I request for a very minimum amount of executors we'll go into the detail what is request and what is remove policy. But you generally got it. So request policy is, let's say a task scheduler has 5 tasks. Okay? It originally got allocated only 3 executors for it. There are 2 tasks which are pending over there for quite some time, for which it needs some executor. And the 3 tasks which are assigned, let's say it's taking more time. So what is the general policy for the request policy is, whatever time span you have mentioned there, spark.dynamicallocation.scheduler backlog timeout, let's say you say 5 seconds over here. It will wait for 5 seconds to see if my pending task didn't get an executor for the time specified in that lot, it will apply a request policy. Let's say give me an executor. So, good.
So when you talk executors and request policy, the resource manager has it already come into picture?
Yeah, the task manager is actually on the resource. Jan is running there, you can assume.
Okay.
The task manager is.
Okay.
Okay. So I'll come into that one. Let me finish this and we'll come. So what will happen is, when he's getting resources, when he gets executors, he doesn't go and like say, give me all the executors for which I have a pending task. That's also a problem. So what Spark does is, it does something like a round robin. It slowly and exponentially increases the request for the executors. That means, let's say we have 10 tasks and only 3 executors we initially got. So in the first round, it will check if all the pending tasks has crossed the time mentioned in the schedule backlog timeout. Then it goes and gets 1 more executors. Then the next round, after the second timeout, there's a second timeout, sustained schedule backlog timeout is there, then it gets 2 executors. Because the design is, there are multi-tenant environment where all of them are sitting and working. I can't go grab for everything and come back because some of mine will eventually get released also. So it's slowly, the second round it gets 2, third round it gets 4. That's how it gradually goes and requests more and more executors to start executing. At any particular point, it says, okay, fine. The remove policy is very simple. I have an executor which is sitting idle more than the time mentioned in the Spark dynamic allocation executor idle timeout. It automatically releases back to the pool. But there's a lot of caveat to this. It's not that simple. And it doesn't work very cleaner also. You can see why it doesn't work very cleaner in the next one. There's something called graceful decommission of executors. Okay. So the executors, how are they gracefully decommissioned? Let's say state, what is the state before dynamic allocation was done? That is before Spark 1.2. Before Spark 1.2, the only case where an executor can actually release back is when the executor itself threw an error, where everything failed and came out, or the entire application got completed successfully. So in both the cases, the executor doesn't have to save the state at all. Because when it failed, there's again the task scheduler initiates to another executor, and it runs the entire task again, recalculates the entire task. So in both these use cases, it doesn't have to actually save any of the state. But with dynamic allocation, this problem is quite complex. The reason is, let's say I loaded a file, I created a filter. This filter ended up in 10 different partitions, and there was one executor which was holding one partition, the task file. Because it became idle for some time till the second one starts executing the second transformation, assume this got released because it crossed the timeout and it got released. When the second guy is executing the second transformation, it will look for its parent information. That node is already released back to the pool. It's not even with it. This case, it's a big problem because now it has to start from the entire top. Because at any point in time, when it caches the data in that particular executor or it writes to its local disk, if it is released back, it cannot actually use it at all. So this problem, is it there till today? Yes, it's there. Spark doesn't have a way to handle this.
So are you saying that the entire transformation has to be executed all over again?
Correct. It has to go to the top also because this is
not for the particular partition separately.
because it already got released. If you are doing dynamic allocation, so dynamic allocation is not a very easy step. Unless you don't need it, you should never enable this guy. By default, it's not enabled in Spark, and it's quite complicated. This one is. This problem is never solved in Spark. But there's one particular use case which is solved with dynamic allocation is the shuffle. In fact, the shuffle is the reason why they solve shuffle is the most expensive operation. If you see, rest of the lineage, even if it goes little above, you can still do it a lot more faster than shuffle. In the shuffle use case, let's say you're trying to bring the data from across multiple parents into one child, right? As part of this operation, this use case, it's a lot more complicated because if I have to run from the parent, usually what it does is it picks up from the disk, the file written on the local disk on the map side, uses that to run the child partition. But since that got released back, I cannot reach that file, so it has to go back and run the entire shuffle, not for that partition alone. Because why dependency we are telling it runs for the entire stack, right? Because for all the parents. That's a very, very expensive operation. Spark 1.2 solves that particular problem alone. So what they did is, usually when an executor on the map side executes it and writes it on the local disk, then that executor starts behaving like a server. So on the reduce side executors, when they ask for data, this behaves like a server and it starts serving the data based on the local file that's written. That's how Spark works on the regular MapReduce. But now this executor, since it got released, the executor is gone, so you cannot ask. So they introduced a new concept called external shuffle service. This external shuffle service is a new process which is sitting on all of the executors. It's a global process, long-running process sitting on all the executors. This process keeps running irrespective of the state of the application nor the state of the executor. And the goal of this process is to serve data to the reduced side partitions based on the file written on the local. Let's take the same use case, where the mapper side particular executor wrote the output to the disk and it got released. So it went back to the general resource pool. When it went back to the general resource pool, the concept of an application is gone, the executor for that application is gone. But the shuffle service is still running over there. Now when the reduce side comes and asks, it asks only the shuffle service. The shuffle service can still have the capability outside of the concept of an application to give this data back. That's the only thing which is solved, which is how it works after 1.2. But the state of cache data, either in disk or in memory, it's actually not preserved. So when you save dynamic allocation, if you're expecting that it will work from the local disk or the cache, it will not work. It will go recompute the entire thing. That's pretty much.
So external shuffle service used in all the cases or only in those cases where the executors have been
Correct. No. Serving thereafter doesn't do, the executors doesn't serve. The moment you turn the allocations on, the external shuffle service once it comes up, all the time only that guy serves.
Okay.
Because otherwise it will be a architecture goes, uniformity is not in the architecture, right?
Yeah.
So it serves from the external thereafter.
So that means it always writes into the file in the mapper state?
All the time it writes to the locals. Yes.
So why is resource allocation so hard? The problem so hard in Spark?
So there is a concept of Spark context which they created per application. So all these resources are actually tied to their Spark context. That's very crucial for them. The way in which, spend a few minutes maybe on this. The way how Spark works in comparison to any other system. Let's say in any other system you're telling, I can go ask Jan, give me this much resource or map and it works, right? Here, the executors or everything is associated with Spark context. A Spark context is associated one per application, if you're running one user per user. Now you can't pass along the Spark context at any level. Everything is tied to that. So let's say I did some interactive operation and you are in the middleware, you received, you gave it to somebody. Middleware web service, you're telling run this query and come back. Then the second transformation you're trying to give it to another guy. You would think it is naturally to learn because from the UI I keep receiving transformations, I can keep giving it to different web servers and do. It's not possible because Spark context, you cannot serialize the Spark context and send it across. So because the executors are tied up to the Spark context, they have to maintain because that's how they run the whole architecture is behind is associating everything to a Spark context. I can do a little bit on fair scheduling if anybody needs it, otherwise I'm pretty much done. We can stop here. So fair scheduling is same as how it's done in MapReduce. So let's say before fair scheduler is done, standard problem. Let's say a first job comes in, all the jobs get resources in a FIFO model. So the first job comes in, let's say the job has 10 partitions and 10 tasks it needs to create. If the total cluster has only 10 executors, the first job will take all 10 and it will execute it. The second job which came in has to wait for the first job to be completed, till then it won't get anything. Let's say there are 10 executors in the cluster, the other use cases, the first job needed only 7 executors. In that use case, the second job can pick up the 3 and do it. So the problem with this scheduling model is, let's say I have a long running task which is running and it needs 10 tasks. The second job which came in is a very, very small job. All it needs is like one executor and done in 1 second. It will never get resources in a normal model. In a fair scheduling, some amount of round robin similar to how MapReduce does. Some amount of round robin, every task gets some level of resources to run it. So in this case, the second task also would have got some portion of it, and it'll pick it up and execute, while the first one is still running.
Okay, so we'll start. Am I audible and then? Okay. So I'll go deep dive in RDD for a start. So I'll go over basics a bit, how to create RDD, what are different operations in RDD, lineage, I'll go into lineage, and there were questions during current sessions. So I don't have deck for that, but I'll address the questions. So I'll answer those. Then I'll go into partitions. Basically, partition is a very key thing for RDD. And then we'll talk about shuffle. So shuffle is the most performance, scalability, and reliability of Spark depends on shuffle a lot. Then we'll talk about type of RDD and how to extend RDD for domain-specific use cases. And then we'll talk about caching in RDD. So, and I'll do a code demo along with that for some of the key concepts, lineage, partition, RDD type, extending and caching. So I'm Satya, I'm solution architect at IBM, and I work in a Spark team here. So RDD basic, I think we covered most of this. RDD is nothing but resilient distributed dataset. A dataset which is distributed, resilient because it provides fault tolerance. So certain partition of data, let's say node goes down or partition got destroyed, again through lineage can be created. And when you say dataset, it's any kind of object. It can be Scala, Python, Java, any language object. It can be user-defined object, and so on. RDD is the fundamental unit in Spark. So basically, everything happens in RDD and around RDD. So how to create RDD, right? So there are two ways to create RDD. You can load from external sources, or you can use collection objects within whichever language you are using, Spark, Python, R, and you can create RDD out of that. So loading from external data source, right? So Spark support a diverse range of file system and file type, be it SDFS, NFS, S3, you can bring data from anywhere. Also provides a way to write data sources yourself, so you can connect to RDDs, you can connect to DB2, you can connect to Oracle, you can bring data from anywhere. Also it supports different file types, right? So that was about file system. It even support different file types. You want to bring JSON data, you want to bring text data, you want to bring sequence or maybe protobuf objects or any kind of objects. So RDD supports that. Also it gives APIs in which you can write custom input or output format, a reader, right? So by default it goes with Hadoop input. If you are in SDFS, it goes with Hadoop input output format, and we'll go more on that, and it reads from Hadoop. But it also exposes APIs where you can extend and write your own input output format and sources. Right? So if you see that sc.text file, this one uses underneath Hadoop text input format. So you can use sc.text file, you can give local file system, you can give SDFS, and you can give a directory with a globe, or you can give a extension like read all GZIP data. Also it reads compressed format. It automatically detects the compression format and reads the data, the text file one. Spark has other more such method and APIs like whole text file, reader for sequence file, reader for objects, and so on. Parallelizing collection in driver object, right? So let's say you have a collection within the driver, you can just do sc.parallelize and it will distribute the data across cluster, and it will create a RDD for you. Now that's about how you load the data in RDD, right? Now we'll talk about RDD operation. So they are broadly divided into two categories: transformation and action. Right? So transformation, so if people coming from Scala or Python background, these are all available. They have map, flat map, you have filter, GroupByKey, ReduceByKey. So when we see MapReduce and compare with Spark, right? So MapReduce has only map and reduce. You have only two operators by the infrastructure itself. You have to write everything on top of that. Spark brings a whole lot of operator up front. both on transformation side, action side, you can combine them, you can merge them together. And with lineage, it brings a really, really powerful language. So we'll even see how big a MapReduce program can become small and Spark, right? So people talk about speed, right? There are two speed I can tell. So one is speed of development and then speed of execution. Spark address both of them. You can write very small code to do a very big thing, which you have to write a whole lot of boilerplate and big code in MapReduce, right? So transformations are lazy. They doesn't actually nothing happens when we execute transformation apart from Spark driver or capturing the lineage. I'll cover more detail in that. So transformations are lazy. Nothing happens. Actions are the ones which triggers the computation, right? So when we do any action, then actually something happens. And transformation always gives a new RDD. So I said like RDD is immutable, right? You can't change RDD. So whenever you do any transformation in RDD, you'll always get a new one. An action returns the data to either driver. You can do RDD.count and you can get the whole count. Or you can write to a storage. So you can return data to external storage, or you can return data to driver. So when you say external storage, again you can go through a whole bunch of data source API where you can direct write connector. You can put data into HBase, you can put data to Solar, you can put data to RDDs and things like that.
Excuse me. Just before this slide, you had these two operations in RDD, right? The text file and the parent line.
Right.
Does those get executed immediately, or will that wait for an action?
Really good question. So I'm coming to that in my next slide. So lazy will listen, right? When we say lazy will listen, and really believe me, apart from action, nothing triggers anything. Right? So transformations are lazy. Nothing gets executed immediately. Only Spark capture or track the transformation, which is also a lineage. Loading data also is lazy. So when I say sc.text file, basically nothing happens. Actually, I can go to cell and so nothing gets executed there. When I do the first action, so let's say I do load through sc.text file, I done like 100 transformations. Actually, nothing happens in the background. And this is really powerful feature, right? Because otherwise development would have been very slow. So I do sc.load, especially in big data, I'm loading a file. Either I have to do sampling or something. Otherwise, if I wait to load the data, I can't do interacting. And Spark Ripple is like really powerful tool for the development. So loading doesn't do anything. It's just the lineage gets captured. Now lazy evaluation. The benefit of lazy evaluation is it reduces. So basically, we tell Spark that do this. So it know upfront the things it has to do, right? So it reduces the number of passes on the data at the end. It groups so many operations together into stages and perform them in one go. Imagine doing the same thing in MapReduce. After every map, it writes data to the disk, spills to the disk. So the burden goes to the developer. You come up with, so let's say you want to do 10 things, but you don't want to do certain MapReduce phases, right, or stages. You have to merge, you have to think of that map, and you have to come up with a complex map logic or code, and then you spill the data. So all burden is in developer. Here, you do just very simple thing, right? If you just want to split a line, after that you want to do some other transformation, you keep doing it. You don't need to worry about it. Spark will do all of the optimization for you. So that is another benefit of lazy evaluation. One thing you have to be, the word of caution is the benefit of lazy evaluation we know, right? But then you need to persist the RDD, because unless you tell, so let's say I did something, right? I executed, I performed an action. I said collect, or I said count. RDD got created in memory, but it doesn't get persisted. So unless I do persist explicitly, next time if I do any operation on that RDD, it will go all the way to the lineage. It may be from loading data all over again, right? So it doesn't persist by itself. So if you fail to persist and you are reusing the RDD, basically there will be a performance pass. It will do again and again. So remember to do that. Now we'll see RDD in action. So again, this is word count, the famous word count. So word count is kind of hello world of big data, right? So here I have sample data, and this is one small program which does a word count. If you remember the word count example in Hadoop, in MapReduce, it used to be like full like code, right? So here what we are doing is reading a data from a text file from SDFS or local. We are splitting the lines by space, and then I'm audible to them? Yeah.
I just want to know when you do persist, should it be along with an action, or it can happen anywhere during the cycle of?
It can happen anytime. So, for example, in this example, finally we are doing a collect. After that, I can say before collect, right? So it needs to be RDD. Collect is extern here. So if you see here, flat map, map, ReduceByKey, all three are transformation. Collect is the extern. So extern doesn't return RDD, but all other transformation return RDD. So on top of RDD, you can do persist anytime. So at that phase of lineage, it will persist the data. Also, there is a concept of checkpointing. We'll see that.
Excuse me. To get the RDD, we should do some action, right?
Yeah, right.
So once after doing the action only, you can persist the RDD, right?
Okay, so if you call persist, it will automatically execute. So persist is one of the actions.
No, actually, as far as I remember, the first time the action is being called, at that time the pursuit of gas, that function.
That is for gas. We'll come on that for details. So things work differently between gas and this thing. I can go in detail, but I have a deck for that. So especially in case of gas, right, the persisting works differently. People think that, okay, I did RDD.gas, it got cached into memory. No, actually it doesn't happen in this case. So once you perform the first action, then the data comes in memory, and from that time on, so we'll see that. So let's go into the word count example. So the sentence is I scream, you scream, let's all scream for I scream. So the flat map will break the words, and then we are mapping word to a one count. You can relate this to Hadoop word count. And then after that, we are doing a ReduceByKey again, like on the Scala language, this thing. So basically, it is taking 2 value at a time and holding it and generating the counts there. And that is the one which is shuffle operation. The earlier ones are like normal transformation. ReduceByKey is the shuffle. I will go into shuffle detail. And finally, I am doing collect. So it will bring all the data to drivers. So collect is really bad operator. You should never do collect for a big data, otherwise your driver memory will not fill. It brings the data which is distributed into a single node. So I'll just run one example for this. And then we'll see how things happen, the lineage and other things I was talking about. So let me go to Spark cell. This is Scala ripple cells. Basically read, tabulate, and then this thing in line by line. So for every line, it does create a singleton. It sends the data to clusters. And again, like you can have different cluster options in Spark. You can go to yarn. So this one is standalone. I didn't say any master here. So I'm copying a setup bunch of. So now I copied the same data. It will execute this. This is the same word count example on a Spark readme file. So we are just doing word count on Spark readme file. And finally, I did a collect at the end. So finally, it returned that string after ReduceByKey we saw, right? So here for each word, we have the number of counts, right? Now let's go to the Spark UI. Spark has a nice UI. I think most of you are aware. So this shows you can get all the detail here, especially for tuning performance and all. This becomes really helpful. They try to expose as much as thing possible here to the developer, so that you can debug better. So this was one job. We'll go into, you can go into timeline of the job. It started from 11:53 and so on. So there were total 4 tasks. The total duration was 5 seconds. 2 stages it came, and we'll see all that in right. So remember there was flat map. Yes, sir.
I mean, in the earlier session we got to know that stages happen only when it's a shuffle.
Right.
It has to happen.
Right.
In our code, what are the 2 stages of shuffle?
Yeah, I'm coming to that. So do you remember the code? Let me go to the code So code has a flat map. These are normal transformation. Excel lines brings a ReduceByKey is the right. So if you see the DAG visualization, which is a really nice visualization of lineage, and I'll answer the lineage question here. So finally, ReduceByKey is the operator which broke the stage, and because of that, there is stage 0 and stage 1. Okay? So first stage does the text file read, it will create Hadoop RDD. Actually, you can go into detail for that. So the first one is Hadoop RDD, and then other two are map partition RDD. So okay, and then you go to ReduceByKey, which is a shuffle RDD. So shuffle RDD is the one which triggers the stage, and we'll go into detail for that more. So this is what lineage is, right? And if I remove the collect there, nothing comes here. So collect is the action which does that. So now there are two stages. Stage 1 at the end of this. So finally there were two tasks, 1 to 3 seconds, other to 2 seconds, and each of them, two stages, sorry, and each of them had two tasks, and it shows how much was the total read and total shuffle, actually 5.3 shuffle, and we'll go into detail for those more. Within this one, within the map task, you can again see the tag, the first stage you can again see the tag visualization. So tail shuffle, it was the first one, you can see the event timeline and so on and so forth, right? So this is really helpful. You can even, so the moment I came to detail of this thing, I mean storage stage tag, you can go into storage tab. When you persist or something, it will show how many partition and other detail you can get here. Now, okay, so this is all about lineage. But coming back to the lineage question in the first session, right? Where does lineage get stored? So in Spark, there is only two types of runtime. So one is driver, and the second is executor. You have remember that Paranth's diagram where I don't have that. So the driver is one of the runtime, and executor is other runtime, right? So who captures the lineage? So whenever we submit a job, driver, unless there is an action, right? Or in a RIPL, I'm writing line by line. So driver keeps capturing the lineage, and once so again so driver is the one which captures the lineage. So unless RDD is persisted, if driver goes down, your lineage goes up, right? So that's why the RDD checkpointing is there. So if you have like really huge number of lineage after, and you have done some work, and after that you want to capture the lineage, go for checkpointing. Or if you do cache also, then you can get away from lineage. But the point is still, if driver goes down, your lineage goes away. It gets lost. Even for driver, you can go to Spark ELB, that object, and then get the block. So they have exposed everything. You can go. It creates a temp file, and whenever you restart context, that gets deleted and degraded. But the point is, for lineage problem, to solve this lineage problem in the Tachyon project, you might be aware of that project where they are working on off-heap memory system, right? So to avoid this garbage collection and all that problem, and you can persist the RDD into Tachyon. So they are working on capturing this lineage in Tachyon. So that is not yet done. The project is under development. Some part of Tachyon has been released. This was prototype, but not fully production released. So once that comes in, lineage gets stored.
So what you're saying is, as of now, the lineage is stored in the driver program, but it's not persisted.
It's not.
So once it's a machine which runs the driver program is down, the lineage is lost.
Right. So that's why you should either do RDD checkpointing or persist when you need it. So you can persist the RDD into SDFS. Once you persist, the earlier lineage is of no use anyway. The next program can, and that is another thing, right? So in Hadoop, you can always share in Spark between two Spark driver, right? You can't share the context, you can't share the RDDs. The only way to share are anything which is in memory, right? The only way to share is that you write into this, and then next program reads from there, like an So that answers the question, right? Okay, so now we'll talk about partitions. So partition is very crucial. So partition is nothing but fragment of RDD. The distributed part, the RDD is broken into partition and gets distributed into the cluster. And fragments allow Spark to execute in parallel, and that's where the parallelization comes into, right? And partitions are distributed across the all cluster where the executors are, and executor picks, the executor selection happens, task and MapReduce selection happens. That allocation we saw in first talk. Now partitioning is very crucial because that impacts the parallelism and how fast, how parallel your job will run, and overall performance gets impacted by that. Right? So how to do partition tuning, or what kind of partitioning is good? So if we go for too few partition, what will happen? So basically, let's say I have a 100 core cluster, but I have only 5 partitions. So I'm not able to use all the code. Overall concurrency or parallelism of the cluster doesn't get utilized. Also, if you go for few partition, lesser partition, you may end up in data skewness. Right? So let's say for certain key the data is too huge, that problem can come. Also, it backpressures the memory for different operators. So for example, there are operators like GroupByKey, SortByKey, OrderBy, which brings all the data into memory because they need to bring. On those cases, if you have few partitions, they will go for out of memory or they will fail. Right? Now this is the downside of too few partitions. If we do too many partitions, right, why not do very large amount of partition, gets lots of parallelism, concurrency, and run faster. Right? So there is framework overhead involved. So in the next one, so there is a scheduling latency, there is network. So if you do too many partitions, you may not get that much data locality. Data has to come through another node. So that brings network I/O and CPU, the disk overhead. Also, context switching is there in CPU because at the end executor is a JVM which is running task into threads. So too many partition is also not good. So you need to balance between the two, and what are the recommended, right? So commonly between 100 to 10,000 parallelism or reducer or partition. Now this is higher than what MapReduce used to have because the triggering a map or reduce is not that costly here. It's like you're not getting opening a complete JVM. The latency is much lower, and that's why you can go for, and things are in memory, and you can go for more parallelism. The lower bound is the double the number of code. So it should go for that on lower side so that you can less utilize the code. And on higher side, think of the data and the time it needs. You go for like 100 millisecond or right. So if it is lesser than that, then you are doing too much parallelism, too much part. So okay. So how is Spark partitions the data? Right. So there are few phases where the implicit partition happens. Right? While you read the input data, how partition gets created. When you do shuffle, right, that is another point where data gets redistributed from mapper side to reducer side, and again get repartitioned. So shuffle is the another. So we'll cover each of this. How does input partition happen? How does shuffle partition happen? And Spark provides custom partition. So you can write your own partition. So you know the domain of your data, your structure, and so on. So you can write your partition. So they give flexibility so that you can control it. Like in MapReduce, remember that setting in split size and tweaking the block size and then cluster block are changed and things like that. Here you can do much better. Now, partitioning input data. So if data is in STSM, Spark uses SDFS input-output format, and it follows the similar approach the way SDFS used to come up with the splits, right, or partition. So, for example, if you do text file, so it goes to text input, text input format class of Hadoop, and it follows the same way. So that has a concept of minimum partition. You can, while giving text file, you can provide the partition if you want text. But finally, there are 3 knobs which control the partition in case of input, and these are coming from MapReduce also. So one is DFS block size. What is your block size? Then number of partition, the parameter you are asking Spark to do the certain number of partition, and third one is the split size. Input is split size. Right? So this is the formula for partition size. And once partition size block size. Block size is deepest block size. The goal size is total input data and how many partitions you ask. That is the goal. So minimum of those two. Now we'll see what happens in different cases, right? So deepest block size in case of local mode is 32 MB by default. Number of partition, if you don't give, it remains 0 if you don't provide in the input, either in text input format or in text file. Text file. So that is 0, means 1 partition. And third one is the minimum split size is 1 KB by default. Right? So if you go with default, and let's take an imaginary case that I have a total data size of 640 MB, right? And if I go default, how many partition it creates? So the formula is max of 1 KB, followed by I didn't provide any number of partitions. So my partition size is 640, and then 32 MB is the default block size. So minimum of those two, it will go for 32 MB. That will be the partition size, and divided 640 divided by 32, you will get 20 partition. I mean, you can do this example in the real cluster. If I want more partition, I have to supply the number of partitions. Right? So let's say if I want 30 partitions. So again, the formula is same, 32 MB, and 640 divided by 30 comes to 32 MB. So you have like on that side 32, so totally you get 32 partitions, even you ask for 30. What if I want bigger size partitions, or like lesser number of partitions? So you need to, so there the knobs are very confusing, right? So if I just ask, okay, give me less partitions. Let's say if I ask 5 partitions in this example, will it work? So once you go to 5 partitions, our goal size is 120 MB, 640 divided by 5, right? The goal size is 120, and then the minimum of 120 and block size will come into picture, and 32 again it will become 30, and I will not get that many partitions. So this is like a wrong ask for partition. What should be the right one, right? So I should increase the minimum split size, because block size I don't want to change. For this problem, I should increase the minimum split size so that you can take the same. So if I go for 64 MB split size here, I'll get 10, which is a bigger this one, using the same formula. And I don't need to try the knob for this one. So if you want to decrease, go for a split size. If you want to increase, go for a number of parts.
Excuse me?
Yeah.
This particular slide is exclusive only for file if it is available on the
Yes.
But what if there are other file systems also support with Spark, right? How is the partition calculated?
Yeah, so when you come up with your custom RDD or any of this one, right? So there is, I'll go into detail for that. There is a partitioner where you can define how you want to. Because SDFS things were fine, right? You have blocks and you can use, these are historical logic, they split block. Even those MapReduce are not MapReduce in Spark per se, they are coming from, historically from MapReduce. So MapReduce things were clear. When you are defining your own, you can write your own custom partition. So, and that will work. Now, let's go to the shuffle mode, right? So, shuffle is the really expensive operation. Data on map side goes into disk, is split into disk, and reduce fetches the data from there. So how does partitioning gets decided? How does partition get decided in case of shuffle, right? So each shuffle operator, most of them, right? ReduceByKey, GroupByKey, aggregate, and combine-by-key, partition by has a parameter. So if you know your data and if you can guess that, you give that parameter. So in that case, it will take that, it will follow that. And otherwise, by default, it goes to Spark default parallelism. So if that is set, in general, you have set your parallelism, it will try to take that. If you have not run the Spark default parallelism, then it goes to the parent. So generally, Shuffle will have parent RDDs, right? Maybe one or more than one. So for example, if it is group by, you are just taking one RDD. If you are joining, you are taking from multiple RDDs. So it goes to the largest of the stream RDDs partition number. So the largest one, how many partition it has. And this they have done to reduce the chances of out of memory. And this was done in very early stage of Spark and is still working fine. So that's how partitioning happens in case of Shuffle. Now, let's say you got the data, but you know how much partition it should be, and you want to tweak that the way the hints or other things are there in RDDs or other thing. You can use repartition. So repartitioning, there are two operators. One is repartition and second is coalescence. So repartition, and then there is a basic difference between the two, and you have to take the right choice there. So if you want to increase or decrease, it supports both of them. But then this goes always for Shuffle. So if our repartition, so have an existing set of partitions and you want to reduce it or increase it, it will do a shuffle like that, which is very costly, right? And if you want to decrease the partition, coalesces, suppose the decrease is specifically, so you should go for coalesces rather than repartition. Right? Now coalesces decrease the partition, and it always try to do narrow dependency. Right? Now we saw the narrow and wide dependency. Now you may not get the narrow dependency in all cases. So let's say I have a node. Each node are having some 500 partition, right? And say I want to reduce like 10 partition each node. It will locally combine the data. So there is no shuffle. It will go for narrow dependency because this is within node it will get that much data. But let's say if I ask too drastic reduction in number of partitions, right? In that case, all the data may not be in a single node. So from 500, if I want to go, let's say 10 partitions or 5 partitions, right? It may have to bring the data into a cross node. So there the coalesces also goes for shuffle. So it try to work on narrow, but if it is not possible, then it tries to avoid the shuffle, but then it may go into shuffle. And you can increase the number of partitions with coalesces also. There is a flag, so it has two parameters: number of partition and shuffle. Shuffle is true or false. You want shuffle or not. You can say explicit shuffle and increase the number of partitions. So you want that. Now that is just the high level. You are trying to change the partition. What if you know the data? What if you know your data structure, your use case, right? So for example, let's say it's a telecom data. You want to break the data into region, sub-region, area, and state, and so on, right? So Spark exposes the partitioner API itself. So you can write your own custom partitioner. You can extend the default partitioner and specify. Basically, for the cases like this where you want to put the domain-specific knowledge, you want to partition by certain things, right? So custom partitioning controls the total number of partition and how data gets distributed. You will get both the options, right? So and by default, even the default partitioner, like as partitioner or range partitioner, they also extend. You can see their code. Basically, they also extend the partition and they put their logic. Right? So basically, there are two things you need to extend on partitioner, which is abstract class here. One is like get partition method. There you have to read logic. So we'll see a code example here. And the second thing is number of partition. Number of partition is another variable there which you have to define, max partition. So I'll go into partitioning demo. Let me just go through the code a bit, and then we'll. Okay, so. So here, this is again same word count example. I'm just throwing the imaginary need of partitioning. Let's say if I want to partition data based on the first character. And let's say I assume I always get to A to Z. So don't go into a use case, just wanted to show how it can be done. Like in real world you may have a different need and you can do that differently. So it extends. So I'm saying I'm writing my own partitioner, which is first character partitioner. It extends partitioner class. And the rule is based on the first character, I will partition in modulo 26 and I want to go for A to Z only, right? So now there are two things which you need to override. At least there are more options as equal to has code and so on, like any standard classes key. So one is get partition, right? This is the core value. This is the method where you have to put your logic. So key is the key on which you want to partition. And key type will be any, so you infer type, so that you can, so to make the method generic, they have done that. And then number of partitions, that is one constant, so you need to give there, so that by default it can go further. So now we are saying, I'll take this thing, I'll take the first character, I'll do 2 upper, I'll change it to integer, minus 65, I'll get 1 to 26, and then I'll do modulo non-partition, right? And in other case, I want to just, don't go into example, but this is how you can write your, so you can put any logic, right? By default, RDDs or Spark has partition logic, or in case of range, it will put range. So now let's, how to invoke that, right? So again, the same word count example. So here we're doing a split, and then I'm just filtering the non-alpha things. So I'm just doing check alpha and throwing away if anything is not starting. Let's say there is comma or call or something. I just want So GroupByKey is one of the shuffle operators. We'll see in more detail for GroupByKey. So now I'm giving the new first character partitioner, the instance of the partitioner which I created into that GroupBy operation. So when shuffle actually happens there, we'll follow this one to partition the data, to bucket the data for reducer. So after that, if GroupByKey returns a RDD, which is a group the RDD. So that comes into partition group. Now in RDD, I'll go into again much detail of RDD interface. You can see the things in RDD, and that will help in troubleshooting or this thing. You can see dependency, you can see partition, you can go in internal to the partition. So there is a method in group data, in RDD, group data RDD, which comes from a GroupByKey. So that is map partition with indexes. So data got distributed, or partition got decided. I want to map them with indexes, right? So with iterator. So now after that, you make that call. Inside that you get partition number and one iterator. So in Spark RDD, every partition exposes an iterator. You might have heard this earlier also. So this iterator is the key thing, right? So be it a cache, whether data is in cache or not, everyone comes whether data is persisted or not. This iterator is the general interface. So let's say my data is distributed across a cluster. Partitions are there in different nodes, and any operation happens on a particular partition, it actually invokes the get iterator of that. And then if the data is already persisted or not completed, everything happens from there. So now I'm getting partition number and iterator there. So I just wanted to show how much, so we use the Spark ReadMe file, right, for word count. I wanted to show like by one character how much counts are there, how much data is going in each partition. So just do iterator.toList, because convert it in place, and do the length. So it will show the count of elements or tuple you can say for each partition. And this itself created RDD operator. So I went there and then I'm giving an iterator there. And that RDD I am just collecting and iterating through that. So group data with partition becomes the new RDD. And then you do collect and I'm just printing it. Right? So I'll run this example. So I have the few inputs already set here. One is the Spark ReadMe file, and second I have given just some local parallel. So now I'll run this program and we'll see what are things it executes. So I could have run in REPL also, but this will run the whole program in one go. So if you see, these are the partition RDD, and you can go and task. Yeah, so basically for each of the first character, we are getting the number of counts. So this is how you can write your custom partition, right? So from 0 to 25, because we are going to alpha this thing, and then count for each word there. I could have printed the word itself. So you can get and see like what is coming in each of the partitions. So that is all about partitioning. Now we'll go to shuffle. Right? So before going to shuffle, one thing I said earlier, right? Spark has too many operators. So, but you need to know which one is best fitted for your use case, right? So, for example, there is a GroupByKey and ReduceByKey. ReduceByKey we saw in word count example. What happens? The data comes to reducer, and then on value side you can give a lambda function. On value side you can give a function how to reduce the data. So, for example, count is coming. You say, okay, keep adding, right? So, or do a sum or do plus. So, GroupByKey on the other side, what it does is actual data comes into reducer side. Like in any other group by, right? So let's say I'm grouping by a particular key, what are the every tuple of that comes to the reducer, and that resides in reducer. On top of group by, you can do certain other operations later on, but you get a group data there. In case of reduce by, you need to tell the function what you want to do, how you want to reduce that. So if you see this example, this is we can achieve word count. The reason I'm showing this is there are too many operators, so you need to know which one to use, right? And the shuffle is the biggest problem, and Because so shuffle is the power, but then you have to use it rightly. So if I do group by key, what will happen is the earlier example only, the maps are having the word and the count. Actual word and count comes to the reducer. On reducer side, I can go into tuple, each tuple, this map function I iterate through each tuple. I can say first field and do all the bucket, all the bag of the second field, right? Do the sum of that. So all the one ka sum. So for example, A 111, we got A to 6, right? A is coming 16. Now here, remember there was combiner in MapReduce, right? We all know. So combiner used to do reduction on map side itself in such scenario. Here we are unnecessarily transferring the data to, at least for this use case, GroupByKey may be needed really in some other scenario. But in this case, we are unnecessarily transferring the data to reducer. And that happens through shuffle. Basically, map splits the data into this, reducer reads data from there, right? Writing to disk and all, especially a Spark kind of system, it's like really costly operation. So now we'll see shuffle by ReduceByKey. So you can do ReduceByKey. In this case, Spark upfront know what is the reduction you want to do, and it will apply that on map side itself. So now mapper itself are doing a local count, which is a combiner in MapReduce world. Right? We'll see more detail on those. I just wanted to show this example, like how much drastic difference it makes. Right? So I'll go to Ripple for this one. Now this is a single node local this thing, right? Local cluster. If you and there is no network IO, there is local disk IO. So I have a data set which is Twitter feed. The size is 163 MB, only 1.5 I'm using. So we'll do word count on this data set by both approach, and we'll see what is the difference in time and what is the real differentiator there in the both approach. Right? So let me just copy paste the code from my DB because I want to run this in the Okay, so first one will run ReduceByKey. Let me just do a clean state UI. So I just close the Ripple and I'll again go and run that. I'll refresh the UI so that we get a plan. So right now, just getting started UI is not yet up. Everything is empty, right? So first we'll run ReduceByKey, word count through ReduceByKey on 163 MB data. Because I'm pasting multiple. Okay, so now it will run this ReduceByKey example, and we'll go into see bonus suffer happen, what time it actually took. So it is still running. How many mapper he created, how many MapReduce tasks he created. Okay, so total time is 17 seconds. Okay. And final number of record, the word count is 1.5 million. Now let's go into the UI. So we got our first job. It total 2 stages. It has 10 total tasks executed across 2 stages. Basically, it took 5 partitions. Yeah, and you can see the DAG. Again, it will be similar word count lineage. You have 2 stages. First till shuffle, and the second is the shuffle. And shuffle is the key differentiator between the 2 examples which I run. So it took around 18 seconds to perform the complete both the stage. 11 seconds it took in the first stage, which does the shuffle. And 6 seconds is the actual count when it does, right? And both ran with 5 this time. And if you see shuffle read here, out of 163, the total shuffle read was 13 MB. And you can go and see more details for each of these. You go into map, you'll see how much actual. You can see the timeline also. So these are the individual tasks, and then finally here, after shuffle, the compute happens. Shuffle read time is 0. Shuffle write time is 19 milliseconds for this task, and so on. So you can see the detail, but key differentiator is see the time here and see the shuffle, right? So this was our job 0 on ReduceByKey. Now I'll run the next one, which is GroupByKey. Because ReduceByKey runs a local combiner and reduce the data locally on the map task itself before sending to the reducer. GroupByKey doesn't do that. Whatever map comes, whatever tuple comes, it just sends. So now it's running here. Go to the browser. That will be job number 1. So still running. Ask another detail.
I have one question. Let's say an application contains 2 actions. Let's say it's the complete code one I'm talking about. So for each and every action, there will be a job submitted, correct?
Right. Unless you persist the RDD, yeah, entire lineage will get, and if you are working on the same one. So let's say on RDD 1 I did a count, right? But I didn't persist. It will run all the lineage on that action. Next time after you did certain other transformation, you did again count. You'll do all over again. So this one took 40 seconds. Now we go to the UI and see what were the key differentiators here. Now we have 2 jobs. The job 1 is the one. So it also created 2 stages, 10 tasks total. So here the map took the same time. The count, right? The reduction on the reducer side took 25 seconds. The first one was almost same, and the total data which got shuffled is 72 MB. So reducer fetches the data and then it sorts and it does count and all that. That costed MB, right? So this is very simple example of a single. Imagine like a cluster of node where your partition is distributed across on that node. You are bringing data, you are doing network transfer, you are writing here, there, everywhere there will go into all that details. But things can go very shuffle, and so we'll do a very detailed this thing on shuffle now. Okay, so what is shuffle, right? So we all know shuffle is the one which takes the stage, and then actual data redistribution happens between partition from map side to reduce side. This is like most of the performance, reliability, scalability in Spark occurs within shuffle. Like with MapReduce, Spark Shuffle also go for full model. Reducer fetches the data from map side, right? And it has been consistently evolved in Spark versions all the way from 0.6, and it's still an open area of research. And people from multiple companies are working on this, all the way from Arise area to Cloudera and Intel. There are guys working on optimizing shuffle. And you remember this Spark beat Hadoop on the petabyte sort, on the terabyte sort, right? 100 terabyte. Hadoop was some 72 minutes. Spark came with 32 minutes. There were 2 or 3 major enhancements. There is blog by Reynolds on that. You can read the shuffle is the one which was the major contributor to that to that increase in performance. So shuffle is very, very important, and whenever you write Spark code, you should keep shuffle in mind. So now what actually shuffle, I think most of us know. Mapper partitions the data into buckets, writes into local disk, reducer fetches the data, and in between there is a combiner like MapReduce. So we'll go into more detail. Like Hadoop MapReduce, it also uses combiner on local side, and reducer fetches the same full model. Right? Now, shuffle overview, I think we know Spark run job stage by stage, and shuffle is the one which is the delimiter for stage. Shuffle dependency calls. There are lots of operators which are shuffle dependency based, like which generate shuffle RDD or co-group RDD. For example, you have partition by, combine by, group by, ReduceByKey, that's the one we saw. And then further in the next stage, there may be other operator which depends on that, and it again create. So for example, co-group output can be read by join and like that. Right?
Excuse me, you mentioned that the compile, like the MapReduce, you can have combiner running on the map task.
Right, right.
In MapReduce, I can override the combiner class and I can write my own code there.
Right.
Can I do that in this one?
I'll go to the detail for that one. What are things are possible there? So shuffle, overall shuffle they are exposing now. So you can change the whole shuffle this thing. we will see in the details in here. So this narrow dependency, wide dependency, and any operator which calls for shuffle breaks the stage, and that becomes one stage in Spark. So I think this most of you know. Now shuffle is expensive. Why shuffle is expensive, right? So shuffle, in case of shuffle, data no longer resides in memory; it has to go into disk. And when you go into disk and do a network transfer, there are certain things comes. You have to partition data. You might have to do a sorting of the data. All of these are like costly operations. You have to do serialization and deserialization data. If you want to serialize the data, reduce the data size, when you are sending it through network and all, you might want to serialize, deserialize, which may be a CPU intensive operation. Also, you want to do compression, again compress, decompress. Or there may be disk IO, right? So remember, Paranth was talking about like Spark started spilling data into memory. No more it's like a just memory-based system. The moment it goes out of memory, it spills the data. So you might have to shuffle spill come into picture by spilling the data into memory to disk just to work, but then you have to bring it from disk, and there may be merging happening on the disk side when you are spilling too many files and so on. So shuffle is very expensive. Now let's go into the history of shuffle, right? So it has evolved over the time. Still there are open Jiras and people are working on it, and still there are lots of discussion going on all this time, right? And still things are getting better and better. So Spark 0.6 and 7, there was no shuffle extra code. The way RDD used to get persisted, the same module used to persist the shuffle. You have the same thing. Intermediate data, you use the same module and write it there. And the same option like in memory, or you can write it this. In Spark 8 and 9, there were two things happened. The shuffle port got separated. They came up with the shuffle block manager and other shuffle objects, block object writer, shuffle fetch client, so on and so forth. Also, they added a consolidated shuffle write optimization. This was done by Paranth. I'll go into detail of that. Spark 1.0 introduced the pluggable shuffle framework. So if you want to extend that, you can leverage that. In 1.1, sort-based shuffle implementation was done by Meetup. So this is the first time the sort-based shuffle, which was there in default in MapReduce, came here. We'll see that one. Native transfer, there are different transfer implementation. And till 1.2 has shuffle was there. So there is a shuffle manager, Spark.shuffle.manager, has used to be the default. In 1.2 they decided no, let's go with the sort. And in 1.5 and going forward, they slowly want to get away from has-been. They might remove the code also. Now, Spark 1.2 also came up with external shuffle services. The way Yarn shuffle, this thing is there for MapReduce, right? So they are also writing this thing so that within a node or within a this thing, you don't need to keep the shuffle objects or shuffle processes within the executor purview. You can separate it out and ask it, use it as a service. So that is coming. Also the sort-based shuffle, there are more optimization coming into that. So I'll go into the detail. So understanding shuffle. So first one is the input aggregation, right? The one combiner we are talking about. And then there are type of shuffle. So mostly there are two types: hash-based shuffle and sort-based shuffle. And it evolved in the same order. So earlier there was a basic hash shuffle. Then they came up with consolidate hash shuffle. And now the latest one is sort-based shuffle. So let's go to the input aggregation. Like MapReduce, Spark also do aggregation on the map side itself, and this helps the data size reduction we saw in the example, right? And the combiner work. So how it happens, right? So it happens in shuffle map task, and it uses two data structure for that. One is append only map, and second one is external append only map. So basically in shuffle you are merging your data, right, for similar partition. So if data is in memory, so these two maps are nothing but they are hash table. Only thing is they are appendable hash table. So you can update a value for a key. So let's say till now count was 5, you are adding 2 more, now it will be 7. Like that. External append only map is a hash table which can spill into disk. The moment you go out of memory, it will write in disk, it will do disk to memory merge and all that resides inside that. It is really, really powerful operator. We will see in sort also. The sort-based shuffle they use. And again, this is append only map, so you can update the value. And this brought the power, like, okay, you don't need to limit it by memory. In earlier version of Spark, if you go more than beyond the cluster memory, your task may fail, and you have to do something to solve that problem. Right? Here, at least now it's still there, and things can go. It will still be better than MapReduce. So in-memory buffer. Next, another structure is in-memory buffer, which is crucial. So while writing files, so basically in Shuffle, what happens? We get the bucket of data partition for a particular reducer. We write it into a file, right? So if you go and write every time, there will be too many disk I/O. So they have a in-memory buffer for that. So they write into buffer, and once buffer gets full, and then it gets stored into disk. So there is a Spark Shuffle file buffer KB parameter which you can set. And this is the one which will lead us how Shuffle got optimized. So first one was basic hash shuffle. Basically hash based shuffle. So hash partition used to happen, data gets bucketed, gets written into buffer first and then in file. The only problem with this is, let's say there is M map task and RDDs task, right? So each map task used to generate one file for every reducer. So for each mapper, you will get R file. Now, how many total number of files are there in this case? M into R, right? So total mapper by reducer, because each mapper is writing one file for each reducer. And how many in-memory buffer you are getting here? So M into R again, right? So that many buffer area in memory you are taking. Also the number of open files, these files are open. So even that count is there. Now let's take an example. Let's say I have a 100 KB buffer size. I've said that. We have 10,000 reducers and I have 10 mapper tasks per executor. Okay? I'm running with this configuration. How much will be the buffer size? So it comes to 100 KB followed by 10,000 followed by 10, basically 10 GB per executor. Now executors are mostly by number of code. So you are giving 10 GB just for shuffle buffer, you will not have much memory for other things. So basically this implementation cannot support 10,000 on this thing. And this was there till Spark 0.9. Right? So now consolidate has then basically they came up with this approach where they wanted to consolidate the number of files. Why to write every mapper writes file for each reducer. So what they did is they went to the file segment format, right? So each mapper, so within an executor for a reducer there will be a single file, and each mapper within that executor will go to their segment and write the data, right? With this enhancement, what happened is total number of file and in-memory buffer got reduced. So per shuffle file per executor is now number of reducer. Right? Earlier it was M into R, now it is number of reducer. Similarly, in-memory buffer is number of reducer. So let's say I have a C code and I have a R reducer, right? So total number of files will be C into R, total buffer will be C into R. Right? Now, but still it is too many files. Take example of 10K reducer again. You have that many open files. You may hit issue of too many open files. You need to go increase U limit, or you may again hit the memory and this thing. And not only that, in between data gets compressed, decompressed, serialized, and so on. So you have to spend too much on this thing, and things are still not better. You can still optimize things here. So that's where they started looking. This idea came from Madai. Why not we are looking at Hadoop shuffle, right? Because their shuffle was there also. So then they came up with this sort-based shuffle, which follows MapReduce shuffle to some extent, not fully. On map side, it follows completely. So what used to happen in MapReduce shuffle? Right? So there was a circular buffer. So each mapper will keep writing the data into their partition in buffer till the buffer gets full. Once buffer gets full, it used to go to the disk, and every time you get a XML file, which may get again combined. Right? So they are following the same. This got introduced in 1.1 and now it is a default shuffle. And this is the one of the major improvement which brought that 23 minute performance for 100 terabyte data and some 200 this thing for petabyte data for sort problem. Right? Now sort-based shuffle map outputs record for each task are kept in memory till the memory fits. Once the memory is filled, then they write into disk. While writing, there is an external sorter. That is another thing here. That while writing, it sorts the data and writes in shortened manner. Now you may have multiple files over the time. There is a separate process which merges them. So at the end of the map task, you will get one file generated from entire this thing. One file generated from map task and one data file, one index file, because you are using segments for each reducer, right? So there will be index file reducer 1, this is the segment, reducer 2, this is segment, and reducer will read from there. Right? Now, if map side combiner is needed with
You're saying like during a spill it will sort and then it will persist into disk.
Right.
So let's say like first spill we did persisted. Then on the second spill again you will have to change whole persisted file, right?
Yeah, so their slight change is there, so it doesn't sort completely, it just sort based on the partition. So let's say you have 5 reducers. So and I get a bucket of data for reducer 1. The data internally for reducer 1 doesn't get sorted. It's not like a full sort. It just sorts based on the partition. And then there is a merge concept. Between files there will be sort merge, which is a separate operation. That happens.
That will be later on.
Right, that happens later on. And so this is high level this thing. And how does shuffle reader happen? So one caveat there is first, so there are few differences from MapReduce still, and these are things they are debating and they are working. So in MapReduce they sort the data completely. Here the data is not getting sorted completely, right? The ones you in Reduce side you used to do a merge sort, right? Then you get the sorted data in Reduce and then you do count or whatever, you get a sequential data in Reduce. Here it doesn't happen. The data is only sorted by partition. And there is a debate, there is zero on that. They are saying the reason they are doing this external sorter is there on reducer side also. And not all the operations will need full sorted data, right? So for example, if you are doing just bucketing data for some purpose, if you want to do group by and let's say sort by, order by, you need the sorted data. So at that time they call external sorter on reduce side. That is next phase. I'll come to it. So basically data gets transferred to reducer, then they will invoke that and they will sort data completely. And this is where people are working and saying that why not sort it completely, because we are sorting it anyway for partition. Right? What is the extra thing? And there are 2 open Jiras. Sandy, few folks from Cloudera and Intel are working on that. So yeah, so it is not fully MapReduce. And another major differentiator is the way things happen on reducer side. So I'll go there. So they didn't change that much. Only the mapper side sort is working the way, to some extent, the way shuffle was working in MapReduce, right?
So is it better because it is not working in that way, or like it is better if it works in that way?
No. So there is redundancy, and that's where they are debating. So this external sorter is inside lots of operators, and that code change is not simple, but people are working, and it will come in the future. It will be like MapReduce. But that's a bit. It is not fully yet reached because of other limitations. So this external sorter has been invoked in certain operators. If you change here, you have to go and change there, and so on. Shuffle reader, right? So I said reader didn't get changed. So the way shuffle read used to happen, the sort shuffle read also happens same way. So basically, reader side both sort and hash shuffle does hash shuffle reader. That code is exactly same. Now, reducer side setup thread fetches the data from mapper for that reducer, and there will be some dedicated thread which deserialize the data and brings into a queue, which is called result queue. And once blocks comes, before giving to the queue, you have to deserialize it. Order by and other operations are there, and this is where there's too much JVM memory gets into use. And then again, those 2 hash tables, right? The append only map and external append only map comes into picture. And if you have operation like sort by key or this thing, external sorter gets invoked here itself. So you have deserialized object in the queue. Now external sorter will sort and give it to the actual reduce function. So this is something which they are enhancing. They are saying when we are sorting by partition, why not sort there? And they have to get rid of external sorter for the operator. Right now that is embedded. So if you go to GroupByKey code, right, or sort by key code, that is embedded inside that. So either you have to change in both place and all that. So they are working. This is soon to come. Once that comes, it will be perfectly fine. But still things are fine because this external sorter comes into picture when there is a real sorting. If I don't need sort, I just wanted to do count by key, right? I don't need to sort. In that case, I will simply do count. Okay. So now we'll go to type of RDD, and before that, let's see RDD interface. So I said like you can go and see inside RDD, right? So basically these are 6 things which are there inside RDD. So first one is set up partitions or split, the way it was in Hadoop, right? So RDD object will have set up partition. Then you will have list of dependency. Basically the parent RDD from where the lineage, right? Lineage gets stored here also. Each RDD know who is my parent. It may be one or more than one, right? Depends on operator. If it is joint, it may be coming from to move on RDD. So list of dependencies. And function to compute, the actual function which you want to compute on the partition. So if you go to RDD paper, right, it says both data and function reside in the same place. Right? This is where the compute invokes that function. And these are three things which lineage gets captured by this tool. Right? Then there is two other optional parameters which some RDD might keep and some RDD might not keep. And this I am talking about because I will go to how to extend RDD, how to write your own RDD. We'll go into that, and that's why I'm going through this. So there is a preferred location for each partition. So for example, if it is a SDFS RDD, you might want to say that this is the preferred location because this is the block. An actual scheduler can give a task to that particular node. So RDD captures that information also. What is the preferred location? And different RDD may keep, may not keep. If it is block based, it should keep. Partitioner define strategy for partitioning. So you can have your own partitioner within RDD, so which defines the strategy. And if you don't, it will go for default as partition. And then there are basic operations which are given within RDD. So map, filter, persist, and so on, so that everyone can use it. Earlier there used to be different RDD for this one. So core RDD, the RDD, actual RDD interface. So if you go to RDD.Scala, right, this is just an interface. Everyone builds it from there. You go to map partition RDD, or you go to shuffle RDD, or you go to Hadoop RDD. Everyone extends that and do certain things. So map, filter, and persist now added into RDD, and they remove those RDD. There are specific RDD just to do filter. The name was filter RDD. So they remove it. Now, if you see Hadoop RDD in real this thing, what does it keep? In partition, it will keep one for SDFS block. So for each SDFS block, we give the partition, right? And then dependency for Hadoop, because this is first read, there is no dependency. Compute, so read the value, right? The reader. And then preferred location should be the SDFS block for that particular partition. And partitioner none. This is like another common one, map partition RDD. So partition will be the parent partition. So the thing I was telling, right, lineage, actually nothing happens apart from capturing the lineage. So it just keep, okay, I will take the data from that Hadoop RDD, which will read from that this block. It captures this one only. This is the partition. This is the parent RDD, and partition I'm reading. Dependency will be one-to-one, the narrow dependency, right? Because only one RDD will read. And then apply map, whatever the map function is, or this thing you apply on parent. Partitioner, there is no preferred location, there is no. It says ask the parent, whatever is preferred for that, and partitioner is none. You see co-group again. So one per reduce task, it will partition data, and could be narrow or wide. And then read and join, shuffle the data. Here shuffle happens. Preferred location none, and it uses has partitioner by default. Now we'll go to extending RDD. This background I was giving because we'll see some of those construct here. So when we need to extend RDD, why not the existing one covers the purpose, right? So when you have a domain-specific operation, right, some transformation or action, this is very, very specific to that domain. And you don't want to write that code using the basic construct map filter all over again in entire code base. The reusability will suffer and maintainability will suffer. So in that scenario, you want to extend and add more operator into RDD, right? Your own business-specific, domain-specific operator. So that is one place where you might want to extend the RDD. You have your own transformation. The next one is domain-specific RDD. You might want to create the complete RDD fully, right? From DB2, I want to do certain things and I want to create my own RDD. You can do that. Or like for a particular purpose, CDR, data and telecom or something, I want to create RDD, I can do that. So this is like database way to express the domain-specific data, a different data set. For example, JSON has a different RDD, and so on, right? So better control of partitioning and distribution. Let's say you want to enforce your partitioning logic and distribution. Partitioning, the way we saw, you can do complete thing in one go if you write your own RDD. And then you can, if you want to add new data source, you can create a RDD from it. Once that links. Now how to extend, right? So we'll go for both of them. So how to add custom operator? So we are using Scala implicit in this case. There is way to extend in Java also, and they are working for other one. And so basically you can add operator into existing RDD, and it will feel like a built-in operator. You are doing RDD.count, RDD.persist. There will be no extra code other than that. Apart from that code you will need for operator, which you do one time. And readability becomes really good, right? Because you're just saying RDD. So we'll see a word count example. We saw the whole word count. We'll just create an operator word count, and I'll say RDD.word count. It will do everything, right? Right now there is no word count in RDD. RDD has all the operator, but not word count. We'll add that. Now custom RDD, right? So extend RDD API to create your own RDD. So they have exposed this custom RDD. You have to implement two things. For sure, there are other things, all the 5 things we saw, partition and all that. So you have to implement compute and get partition abstract method to extend RDD and create your own. Let's go little bit on implicit. I'll just cover only for this one. This is the Scala thing, and you can read in detail. So basically, it creates an extension method to existing type. So you have a already defined class. You want to add few more method to that, or in certain parameter you want to add an implicit parameter. Want to add it there. So there are different needs for implicit, and here we want the reason we are using implicit is like RDD is existing, right? But I want to add an operator to it without changing the actual RDD code. This operator I need just for certain purpose. I have a big set of operation which I want to do in one. So we are using implicit classes. I am using implicit has parameter, conversion, and classes and so forth. This got introduced in 2.10, Scala 2.10. There are different approaches to do that. You can go with method implicit. So the example which I went with the implicit class. This is much simpler one. And okay, so implicit gets translated at the compile time itself, right? Resolved into class definition, actual class definition. So for us, this is like a sugar, this thing, syntax sugar, where this is just for us, but after compilation itself, it gets converted into complete this thing. So we'll use implicit to add new method to the RDD. Now, how we'll do that, right? So this is Scala feature, this is not a Spark feature, and operator will show in RDD like a built-in operator. So let me go to the example for that. So custom RDD operator. Okay, so I'll just go over the extension part, and then we'll see that we'll be able to do RDD.word count. And this is the same RDD which got created through sc.text file. So sc.text file, I did RDD.count. I will show the number of count, and then I will do RDD.word count, which will show the output of the number of tuples in the actual word count example which we saw earlier. So all that word count example code you don't need to write. You just say RDD.word count, and you will be able to do it. So how to do it, and you can add any number of functions, right? So for implicit to use, right, when you use implicit class, it needs to be within an object or package object or class. So we are using object here, and this is implicit class. I'm just creating an implicit class reach RDD, okay? Passing it the actual RDD to this class. And within this implicit class, I'm adding few methods. Once this implicit gets applied, this method comes like a built-in method to the RDD. It behaves like a built-in method to the RDD. So for example, word count, right? So I'm adding a method word count. This RDD is a text string-based RDD. You do the word count. And I'm splitting the line into space, based on space, mapping word to count, and then doing ReduceByKey, and finally getting a word count, this thing, the word count RDD. You can say count line width. So let's say a particular string you want to search in the Spark RDD file. You just say, okay, this give me all the line which has this string, right? So it will give the count. So you just do this, and then you have to say import RDD.implicit. So this entire RDD implicit object gets imported, where this class gets applied automatically. So this so the main thing which makes this class gets applied is the parameter. What parameter this class is taking? It takes RDD parameter. Now anywhere you have RDD, it gets applied, and you will get these methods in that RDD. So we have RDD here. This is RDD type. The moment I say import RDD implicit dot underscore, while compilation itself, it will add this method to the RDD. Again, the example is same Spark context. We are reading the Spark readme and just printing read count once. Then I am doing RDD.word count, which we defined, which is again like flat map, ReduceByKey, and then count. And then next example, I'm saying count line with this Spark. Give me the lines which have this Spark. And there we did a filter on this string and there is a count. So you know this. So there's too much rows here. So let's go from first. So this is the actual input file, which has 98 lines. The first RDD.count we did. This is the actual RDD operation. And then we did a word count, which generated this RDD in one go. Get this RDD. The last one we did a search on Spark. Give me the line which has a Spark in it. We got 18 lines in Spark readme which has a Spark in it. So this is one example how you can put your own operator for your domain need into RDD. Now let's go and see how we can create a complete custom RDD. So extending RDD allows you to create your own custom RDD, especially if you have a use case or data structure which you want to represent, you can use that. Custom RDD also allow you control on computation, change partitioning logic, or even you can give your own locality function. I think there was a question, right? Hadoop has this data block and this thing. So you can leverage all those things using these functions for your own data set, your own system, and create a RDD over there. Now just go to the custom RDD example. Okay, so again I'm just going to alphabet example. Where I'm just creating a RDD, which is alphabet RDD, which so you read data from disk, right, in text file, and Hadoop RDD you get that data as a RDD of string. So here, just after reading, I want like capture only tuples which has alphabet in it. Anything which has comma or something, I want to throw that. My data set itself, I want to read a file, but throw everything. Just keep the one which starts with alphabet. The example we saw. Again, don't go to use case. I'm just using this one to show the feature. You may have a real use case in domain and where you want to do. So here we want to read a file, throw everything away which has other than alpha in the beginning, right? So to create your own RDD, you have to extend the RDD class, and here you can control.
It's not presentation.
Oh. So here I want to do this only for string type of RDD. If I want to make it generic, I can do that. If you want to control, okay, only for this type you apply that, you can do that. And again, you can use implicit to add syntactic sugar. You just define this custom RDD, use normal RDDs. The moment you write this and say implicit, the normal RDD will get this function, partitioning, and all that features. So you have to include the library, and then RDD is working for you the way you want it. Right, or it became customized for you. So two things which you need to define for sure, and other things you can leverage the partitioner. So one is the get partition method, and second is the compute. So when you extend RDD, you have to write this. And most of the RDD, if you see pair RDD or any RDD, you'll able to see this override happening there. So here what I'm doing is just after getting the data, split it into words, and then check for the alpha and keep only those. So my RDD become a tuple where each words are tuple, and only those words which are beginning with alphabet are there. So that is the compute. Now that became my RDD, though I read from text file. Right? Partitioning, I am not doing anything here for this demo, but you can use your own logic and your own way to partition the data. Also, you can extend other functions also. So, and this one just there is a check alpha method which takes this string. So basically, so when you extend the RDD, you get partition and you get task context. These are the two operators, and this partition is also known as a split for the historical region. And so once you get these two, and then you have to write the compute where you take the base RDD, the parent RDD is split and partition, iterate through that and do something or some computation on that. That defines your compute, that distinguishes your RDD with respect to that one, right? So here it's just taking the first parent, which is the base RDD will pass either through implicit or explicit. The first RDD, and I'm taking the iterator, I'm taking the split, which has a split in context, and then just the Scala tag map on the line. Basically, that becomes a list, or iterator has a list. Now I'm just doing flat map on that. Every line I'm breaking into words, and then again I'm doing a filter. So this is operation happening within a split, within a partition, a party, not like a complete RDD operation. So the another use cases where you might need to do this is, like, let's say you have some operator which triggers the actual execution, which avoids the laziness, right? Then you might want to come through the extending the RDD itself, where you can still adhere to the laziness. That is another use case. You have another input source and you want to write all the way different RDD, you can use this. Now, in the code, what I am doing is, again, the text file has RDD. Here I didn't use implicit. I am just passing the RDD and getting a new alphabet RDD, which is of type alphabet RDD, and I am doing count on that. And then we'll, so first one will give the line count in the readme file. Second one, since we have modified the RDD, we made it a collection of word, it will give the word count.
But this complete method will also be called an action, right?
No. So in this case, yeah, this is the count method of actual RDD. So count invokes the compute. So this is action. There may be scenario where you want to do a certain operator in lazy way. If you don't go with the complete extending the RDD, right? If you go with the operator, you saw the earlier example in operator, we went into the actual MapReduce RDD operator. I said RDD dot, so if I go to that example. So the main differentiator between this approach and we are actually invoking the real operator of a map and reduce and all that, right? So here if I say any action, I don't have control. Basically it will invoke the action. But if you want to implement that in a way where you want to keep it for a lazy thing, you can do through extending the RDD. So one example I can give is drop, right? So Scala has a drop method for collection. So where you can drop a particular element within a collection. So if you want to go with the just operator implementation, it will always boil down into action, because you don't know the collection until you run the lineage, right? But extending RDD, I can implement drop without triggering an action. So there are scenarios where you might want to do that. So that is one of the use cases actually. There are different things, right? You just want to have for input file or input source, you might want to have for representing your domain specific data structure and so on. So, okay, let me run this example. So we were in this. The first one is the total number of lines in the file, and has alpha in there, so that came to code interview. Other record which has alpha words in there. So this is how you can customize an RDD. And you can see your best thing is like the few of the RDD you can really read, and they don't have much of code after you know the RDD abstraction. And that if you have a use case where you want to write RDD, just go and read the map partition RDD, the simplest one. It has like some 10 lines of code. That's it. Apart from basic RDD, you can read the pair RDD and things like that. Now, last topic I want to cover is caching in RDD, and that there was a question, right? When actually this caching happens. So this will answer all those. So Spark allows caching and persisting entire data set in memory. It is your choice. If you have really a use case where you want to keep the data, it will be very frequently looked upon. Then you can persist in memory and keep looking on. There, the Tachyon project is coming where you can avoid the garbage collection and all that. You can keep the data off field. So things like that. So it allows that. Persisting RDD cache, right? So how it happens? So when I say RDD.cache, nothing happens. First time when it is computed, then it goes into memory. First you compute, then it goes into memory. Next time onwards, it will use it. So till the action perform, it doesn't, cache doesn't invoke. It just tells the driver that this is going to be persistent. And reuse the cache partition in next test operator. It is fault tolerant. So let's say if node goes down and the cache is gone, right? The cache partition is gone. It will recompute again in the first need, right? So anyone invokes the iterator for that partition first time, it will see whether it is in cache. I'll show you that code where it goes to cache manager and say check if that partition is in cache. It is there. It will give. Otherwise, it will compute the lineage, bring the partition into cache, and then give you the data. Caching is key tool for interactive and iterative processing, which brought the whole RDD concept and Spark and so on, which are the bigger pain points in MapReduce. So, and persist support different storage layers. So you can persist in disk, you can persist in memory. Now with Tachyon projects, you can persist in Tachyon memory. You can persist the ways, different ways, serialized versus deserialized. All these choices are there, and there are recommendations where each has their trade-offs, right? So if you serialize the data, the I/O will be faster, but then you have to deserialize CPU will go some CPU cycle you have to give, and so on and so forth. So there are recommendations in the Spark wiki itself, those things. So I'll not cover that. Now caching in RDD, right? So Spark context track the persistent RDD. I'll actually show in the code. You can go into Spark context and say, give me the RDD which is currently persisted. So Spark context captures that. Block manager puts the partition in memory. So block manager comes into picture. It puts the partition into memory. Cache is also lazy related. No caching without an action. So and shuffle also. So that is explicit caching. Sometimes if you see again this one also in the example. Sometimes shuffle also keeps the data in cache. So you run a shuffle operation and then go to persistent RDD. You look into cache. You're able to see that there are some blocks from shuffle. But then that will get kicked out if there is a real cache need. This they do just for optimization purpose also. I'll go to the demo for caching, and that will be the last. So again, if you start with text file, we are reading the word count file, we are doing the ReduceByKey. Finally, you get a word count data set, right? Here are RDD which represents the word count data set. Now, if you see here, if you go to word count and partition and head, that will give you the first partition. We just want to look inside only one partition in that. So we're just taking that, and then you say word count dot cache. Do this really cache that? The next line will say that check persistent RDD. The moment you cache or persist RDD, basically you will able to get from the Spark context that give me the sc.get persistent RDD. So here, even though I did a cache, till now there won't be any RDD persisted. But when I actually run an action, right, which will come later, before that, again, we are going into block manager also and see that if something is cached. So now block manager you can get from Spark env. Spark env is the guy which keeps every manager, any daemon, not daemon person, resides inside Spark env. So you can just go to REPL, say Spark env.get, you'll get shuffle manager, shuffle block manager, and so on and so forth. So we are just getting block manager here because we want to see inside block manager. And then there is a whole set of Spark storage classes. So anything related to storage, right? If you want to learn and understand, you can go inside this storage package and see the classes there. So all these Tekion things are also coming there, where they will capture the lineage, store it there, logic for that, logic for putting the block in Tekion and all that. So there is a RDD block ID, which is for each RDD there is a block ID, which you can create that through if you want to create for a RDD. So for word count we created our final RDD was word count, right? We did certain flat map, ReduceByKey. So from word count you get a RDD ID, and also we went into partition and get the first partition. So we are getting an index of the first partition. Now these two, the ID and index of partition, defines the block. So here we created a block ID. You can go to block manager and ask the block manager, do I have this block really persisted there in cache, right? So block manager.get block ID will go and check, do I have this, because block manager controls the caching, right? It caches the block and it knows that I have cached it. So till now we haven't performed the action, we just did cache. It is not there in actual cache. So this one will say no, this ID is not there. Now I'll do word count, which is a real action. Now if you see sc.get persistent, check persistent list of RDD list after action, you will get that okay, this RDD is persisted now. And then if you ask block manager, it will return okay, I know this RDD, I have persisted. So let me run this example and